Yeah. It's my great pleasure that to open our autumn school advances in decision analysis, and the first speaker is Arunava Sen, is a very good friend of mine, professor of Indian Statistical Institute. Arunava got his grades, master grade in Oxford, in Princeton, PhD, right? Do I remember correctly?
Yeah, yeah.
Yes.
Yes.
So, and he is one of the leading scientists in our field in the world. So it is my pleasure to give him a floor. Arunava, please go ahead.
Thank you, Fuad. Thank you for inviting me to the summer school. Good morning, good afternoon to everybody. Hello, Amit. Good to see you. So, um, okay, so this is a talk about sort of matching and fairness. And it's joint work with several people, two of my students, Sonal and Shomendu, my colleague Devashish, and my friend Jay Sathuraman. So, so the first slide is just a problem. Okay, so there are teachers and there are schools, and each teacher is initially assigned to a school. This is history. For whatever reasons, teachers are in some schools, and school J needs NJ teachers and is assigned EJ teachers. And surplus schools are those schools J for which EJ is greater than NJ, and deficit schools are those J's for which EJ is less than NJ. So the first one is EJ greater than NJ, EJ less than NJ. And the question that we wish to address is that what is a good way to redistribute teachers to improve this initial assignment? Okay, and uh, to come to the conclusion, if you will, we want to tell you that at least in our model there is essentially one good way to do it, and perhaps only one good way. Okay, so so some motivation. So the ratio of teachers to students in a school is an indicator of the quality of education. And in India, schools differ widely in teacher-student ratios. And I'm referring here to state schools or government schools. And there was an act passed in India in 2009, which was called the Right to Free and Compulsory Education Act, or the RTE. And it said that government schools should maintain prescribed teacher-student ratios. Okay, and obviously the ways to improve teacher-student ratio was hiring, consolidation, and transfers. And here we will focus attention on transfers. So let me, just read a few sections of this act in order to motivate our formulation of the problem. And the section 22 says the sanctioned strength of teachers in a school shall be notified by the central government, appropriate government, or the local authority. The central government, appropriate government, or the local authority, as the case may be, shall redeploy teachers of schools having strength in excess of the sanctioned strength. So it's written in the usual bureaucratic language that you have in India, which we've inherited from the British. Uh, so a few words, yeah. A few words of a little bit of background. So, education in India is what's called a state subject. There are 28 states in India, and states can formulate their own policies in the general framework of the RTE. So you could transfer teachers without taking um, their preferences into account. You could just tell, teacher A, go to school X, whether you like it or not. But if you transfer teachers without taking their preferences into account, then in India you have many ways to stall the procedure by going to court and doing various things. So it seems like a good idea to take preferences of teachers into account. Okay, and in fact, for the particular state of Haryana, which is in northwest India and adjoins Delhi, so its vision statement says the policy is designed to ensure equitable demand-based distribution of teachers, heads, to protect the academic interest of students and optimize job satisfaction amongst its employees in a fair and transparent manner. So I'm drawing your attention to the word job satisfaction, which we take to mean that you should take preferences into account, preferences of teachers, and fairness, and these are words which are used. So what do we do in this paper? We formalize a version of the teacher transfer problem, and we reformulate this problem as a network flow problem where teachers have dichotomous preferences. And we define fairness and efficiency of outcomes in a natural and unambiguous way, according to us. And finally, we show that these fair outcomes can be achieved by a strategy-proof mechanism. Okay, so that's the outline of our paper. Okay, so let's talk about our model. So each teacher finds their initially assigned school acceptable. I mean, this is kind of a definition rather than anything else. And we assume that teachers can only move to schools they find acceptable. So this is an individual rationality for teachers. You cannot force them to go to a place, far away from where they, are originally formed, and so on and so forth. And so here are some other assumptions which we make, which we believe are reasonable. So teachers can only move from surplus schools, right? Otherwise, you could imagine a general problem in which teachers can move from both surplus and deficit schools, but we will just assume that teachers can only move from deficit schools, and teachers can only move to deficit schools. Okay, again, this is an assumption. It's easy to construct examples where you can achieve better outcomes by allowing movement from surplus teachers from surplus to other surplus schools and then on to deficit schools, but we are abstracting from that. And no surplus school can become a deficit school. You cannot make a surplus school transfer so many teachers that it becomes a deficit school, and no deficit school can become a surplus school. Right, and we can find justification in that RTE document and so on, and so only the teachers assigned to surplus schools can move. Let me also say that some of these assumptions can be relaxed pretty much using the same methods that we are doing. I don't think the results will change qualitatively. Although they may actually change, quantitatively. But okay, so this is some justification, for our assumption, and again, we in the paper discuss extensions where these assumptions are relaxed. So let's come to the model. Okay, so the set of deficit schools is D1 to DL. The set of surplus schools is S1 to SM. T1 to TN are teachers, and each teacher is initially assigned to a surplus school. Its owner, shall we say, O of TI, which belongs to the set S. And W of SJ is the set of teachers initially assigned to SJ. Okay, fine. And here is a critical element of our model. Each teacher has a set of acceptable schools, ATI, which is a subset of T. So these are the schools which he or she can be transferred to. We allow transfers only to these schools. And now for each deficit school DK, we let beta of dk denote the deficit of dk. And so we have a deficit vector beta, which is just a list of the deficits of all the schools. And likewise, we have a surplus vector, which simply lists the vector of surpluses for each school. So now we have a teacher transfer problem, which is this tuple, which consists of the set of deficit schools, the set of surplus schools, the set of teachers, the acceptable sets for each teacher, the deficit vector, and the surplus vector. And this we denote by a gamma. Okay. And what is a transfer? So this is the formalism, but it's a map from T to D union S. So a teacher can only move to schools that they find acceptable. So you either get transferred to a school that you find acceptable, or you stay in your initial assignment. No surplus school can become a deficit school post transfers. That's the second bullet there. And no deficit school can become a surplus school post transfers. Okay, so this is these are the 3 bullet points. I mean, it's I don't think the notation is particularly important, but this is what they say. This is what those the notation is saying. Okay. So what we're interested in is the post-transfer deficit vector. And let capital sigma be the set of all transfers. And every transfer generates a post-deficit vector of post-transfer deficit vector beta of sigma. And what is that? That is simply your original deficit minus the number of teachers you transfer to that school. Okay, so that is the post-transfer deficit. And our planner is interested only in the achievable post-transfer deficit vectors, nothing else, right? So we are not saying anything about the preferences of either surplus schools or deficit schools. So we are making important assumptions, but there is some justification if you look at the actual document for schools in various states in India. Okay, so the question is, what are the reasonable objectives of the planner in this model, right? What post-transfer deficit should the planner seek to achieve? And our contribution in the paper is that there exists an objective which you can say subsumes all other objectives. Okay, so here are possible objectives. A utilitarian, so you minimize the sum of post-transfer deficits. In other words, transfer as many teachers as possible. You can have a Rawlsian objective, and which is to minimize the maximum deficit. And you can have lexicographic versions of the Rawlsian, which is to find a leximin deficit vectors where deficits are arranged from largest to smallest. So you try and minimize the maximum deficit. Once the maximum are the same, you go to the second one, etc., etc. And in general, you could have a welfare maximizing objective, which is to minimize the total loss for a continuous and convex loss function of the deficit. So, these are possible objectives. And what our result shows that for this problem, for the problem as we have formulated it, there is a single transfer meeting all the objectives. That is our result. And let me again, at the cost of repetition, just point out that in general, for an arbitrary problem, there is no reason for these objectives to be compatible. For instance, if the set of feasible deficit vectors is 2 beta 1 plus beta 2 is less than 30, then the utilitarian solution will be 0, 30, and the lexicographic solution will be 10, 10, right? So it's not a surprise that these are points on some frontier. The utilitarian one is not going to be the same as the Rawlsian one, etc., etc. In general, this is not true. But what we will show is that we are able to produce amongst all the post-transfer deficit vector, a deficit vector which actually Lorenz dominates all other transfer vectors, post-transfer deficit vectors, right? So let's just introduce the terminology, which is familiar to all of you, but let me repeat it anyway. So suppose we have a vector gamma in L-dimensional Euclidean space. So a box of gamma is the vector of the components of gamma, where the components of gamma are ordered from highest to lowest. So gamma 1, gamma L, where gamma 1 is greater than or equal to gamma 2 is greater than gamma L. And we say that for every gamma, gamma prime, gamma Lorenz dominates gamma prime if the partial sums of these ordered vectors are all arranged in this way. So in particular, gamma 1 is less than gamma 1, gamma prime 1, gamma 1 plus gamma 2 is less than equal to gamma prime 1 plus gamma prime 2, etc., all the way up to L, right? So so this is we say that gamma star is Lorenz dominant if beta gamma star Lorenz dominates beta gamma prime for all feasible vectors gamma prime, right? So using words which may be familiar to some of you, the vector gamma star majorizes the deficit vector from gamma star majorizes all other feasible Lorenz majorizes all other feasible post-transfer deficit vectors. And it's kind of we know that if such a Lorenz dominant transfer vector exists, it reconciles the utilitarian Rolzian lexicographic and welfare maximizing objective, right? I mean, you can see that immediately that these are well-known these are well-known facts. The point is that you do not expect a Lorenz dominant element to exist, right? And our basic result is that for this problem, a Lorenz dominant policy or post-transfer deficit vector exists. That is our result. Okay. And so this is our theorem, our main theorem. So which says that there exists a Lorenz dominant transfer for the TT problem, right? And I think that what may be of some interest is to give you an idea of how we prove this, right? So what we do is that we provide in this talk, I'll provide a roadmap to prove the theorem. And the basic point is that we can formulate the TT problem as a single source, multiple sink network flow problem, okay? And conduct our analysis in this framework. Okay. So, rather than going to the formal stuff, let's actually look at an example. So here is an here is the example of a particular teacher transfer problem. So here is a graph. So I will say N naught here is a source node. And then we have the sink nodes, which are the deficit schools. So there are 7 deficit schools, D1 through D7. And we have a deficit of 5 in each of these schools, right? And then we have the surplus schools, S1, S2, and S3, which are the nodes which immediately succeed the node N naught. And then we have the teachers who belong to these schools. So T1 belongs to S1, and T2 and T3 belong to S2, T4 and T5 belong to S3. And then there is an edge between a teacher and a school only if and only if the teacher finds that school acceptable. Okay, so T1 finds D1 and D2 acceptable, T2 finds D2, D3, and D4 acceptable, and so on and so forth. Okay, so this is a description of the edges. Now let's talk about capacities of the various edges. So the capacity of an edge from S1 to N0 is simply the surplus of that school. It's simply a surplus of that school. That is the maximum number of teachers it can transfer. So, I mean, we have here a special case where, in fact, the number of teachers who want to be transferred is exactly equal to the number of teachers who can be transferred. So, for instance, S2 has a surplus of 2, and there are exactly 2 teachers, T2 and T3, who are willing to be transferred. But in general, the capacity of the edge and not S2 could be 1. So although there are 2 teachers, T2 and T3, who wish to be transferred, you can only transfer 1, given our assumption that you cannot transform a surplus school into a deficit school. Okay, and of course the capacity of each of the edges from a surplus school to teacher is 1, and the capacity of an edge from a teacher to a deficit school is also 1. Okay, so what are we interested here? We are interested in a flow. So what we're interested in is, so imagine this is a network which we are trying to transport water from N0 to the edges D1 through D7. And these are pipes, and the capacities of those pipes are as labeled in the diagram. And what we want to do is we want to see how much liquid we can transfer from N0 to the edges, given the some important constraints that we can never exceed the capacity of an edge, and also that other than the terminal, than the source and the sink nodes, there is flow conservation. So to any node which is not a sink or a source, the flow into that node must be equal to the flow out of that node. Okay, so I have described all the stuff here. I'm not going to do not going to go through the notation. Now we're going to consider 2 problems. We're going to consider an integer flow problem and a relaxed flow problem, where we can actually transfer fractions of teachers and so on, right? So we let script F be the set of integers, integer flows in G. So each of these flows is restricted to be an integer. And gamma I is G of script F, which is the integer network flow problem. And the point is that every transfer, as you can see, it's not it's almost obvious that every transfer integer network flow problem can be identified uniquely with a teacher transfer problem. Okay, so a teacher transfer problem is an integer flow in this network problem. But in order to prove results about the integer flows, we will actually consider the relaxed network flow problem, where gamma R is equal to G of F tilde, where F tilde is a set of function flows from E to the non-negative set of reals, right? Satisfying the earlier condition, right? So in this relaxed problem, we will allow fractions of teachers. So teacher can be transferred with probability half, let's say, to deficit school D1, and with probability half to deficit school D2. This allows that gamma R. Although our goal is to prove results for the integer network flow problem. And since observation, gamma I and gamma R use the same network G, and script F is a subset of script F hat. It's clear. Okay. So what is our proof strategy? Well, step 1 is to show that there exists a flow F hat in F tilde, which is, I remind you, in the relaxed network flow problem, such that the post-transfer deficit vector resulting from F hat Lorenz dominates all post-transfer deficit vectors arising from flows in F hat.
Sorry,
Yeah.
sorry, Arunava, I
Yeah.
missed one perhaps very important thing.
Yes.
Is it possible to have not integer flows, some real values?
Yes. I mean, in general, we can allow for relaxed flows. I mean, this we will not actually allow in our model. Our model does not permit that, but this is how we will prove the result. So this you can think
Okay.
of
Because
as
this was so real, I understand that, for instance, sorry for interrupting you, but
no.
in our seminars we allow to interrupt any
Absolutely,
moment. Yes. And
please.
I thought about that maybe, for instance, if I'm living in Moscow in some district, I can work in two schools, for instance, 3 hours in one school, 5 hours in the other school, for instance.
No, we are not actually allowing that. And in fact, the results will, is to show that we don't need to do that.
Okay.
So that is going to be our result. So we will show that we will consider a relaxed problem, and then we will obtain from it an integer solution to the problem.
Okay.
Okay, in a suitable
Thank
way.
you.
Okay. So we step one is to show this property in the relaxed flow problem, and the second step is to round or approximate. I think round is the term that we use that is used. Round the flow f hat to a flow f in script f, so that f Lorenz dominates all flows in f. So this is an important point. If we round a flow, so we make it an integer flow from a relaxed flow, then it is not necessarily Lorenz dominant amongst all flows in the relaxed problem. But however, we show that it Lorenz dominates all other integer flows. Okay, so it Lorenz dominates all other teacher transfer policies, right? It does not dominate all other vectors which can be achieved by a relaxed flow, but it dominates everything else which can be achieved by integer flows, right? So it is Lorenz dominant in the class of teacher transfer policies, what we permit, that we do not permit fractional appointments and so on. Okay, so that's what we are going to show. Okay, so now we return to step one, and which is to demonstrate the existence of a Lorenz dominant flow in the relaxed problem. And so here we follow a classic paper of Megiddo in 1974 in math programming. And the ideas are very interesting. I mean, the mathematical techniques and what we do, and we follow Megiddo in this respect, is we construct a cooperative game W from the network flow problem. And then following an algorithm from Megiddo and actually from a paper by Datta and Ray in Econometrica in 1989, we use this cooperative, we use an algorithm which was proposed by these guys to form a Lorenz dominant flow, to find a Lorenz dominant flow using the properties of W, right? Against this is in the relaxed problem. and so let's, and then what we will do is that we will then round it or approximate it to integer flows. Okay, so let's dive into the details, if you will. We are going to construct a cooperative game we are going to describe a cooperative game from the relaxed network flow problem. So how are we going to do it? We are actually going to think of the deficit schools as players. Okay, so there are as many players as there are deficit schools. So let's take an arbitrary subset B of the set of deficit schools, and let VB be the maximal flow into B using flows in F hat. Recall that F hat is a set of all relaxed flows. And formally, VB is max of the flow from the source node to any sink in B. And an observation here is that VB is an integer for any B subset of D. So why is this? From the famous max flow min cut theorem, VB is the capacity of the minimum cut separating N naught from the set of sinks in B. And since all capacities in gamma R are integers, VB is an integer as well. Okay, so VB is an integer for any subset B. Okay, so from VB, we can construct WB, which is the lowest possible deficit for B using F hat. So this is the, if you look at the set of schools B, what is the lowest possible deficit that we can obtain from B using all flows? And WB is the summation of beta dk in B, which is actually the set of deficit schools in the set B, minus V of B, which is the maximal flow into B. So it's the total deficit that you begin with minus the maximal flow into B. And so WB is also an integer because I've told you that VB is an integer and the set of deficits to begin with is also an integer. Okay, so let's actually return to this example and show you by brute force what these B values are. So suppose we look at the set. Let's just consider a particular case of D1 and D3. Let's look at this set, the subset of the set of total schools, which is D1 and D3. What is their initial deficit? It is 10. How many teachers can you transfer to D1 and how many teachers can you transfer to D1 and D3? Well, you can transfer 3. You can transfer T1, T2, and T3. They're willing to go to D1, what did I say? D1 and D3, right? So the WB is equal to 10 minus 3, which is 7. Okay, and you can do this for every subset of schools. In particular, if you look at the set D1 through D7, that's 1, 2, 3, that's 35. The initial deficit is 35. How many teachers can you transfer there? You can transfer all 5 teachers there. Okay, so it is actually 35 minus 5, which is 30, right? So W of the set of all integers is 30. Okay. Okay, so here is some important properties of W. That the deficit, here's a definition. A deficit vector H is achievable if there exists a flow, a relaxed flow, such that the post-transfer deficit of school K is beta of dk minus f of dk. Okay, so you can achieve this post-transfer deficit. Okay, and now we can essentially rely on the Megiddo theorem result to say something which is something quite interesting, which is that a vector H is achievable if and only if H of B is greater than equal to WB for all B subset of D. So in other words, here is a better way of saying it. A post-transfer deficit vector is achievable in gamma R if and only if it lies in the core of this game, right? So we have defined a cooperative game, and we have said that a post-transfer deficit vector belongs to this, is feasible. You can achieve this post-transfer deficit vector if and only if it lies in the core of this, transferable utility game that we have defined, W. Okay, so just a brief remark about this achievability, about this thing lying in the core. To see that that these inequalities are necessary is not difficult at all. It's almost obvious, but to show that they are sufficient is slightly more, subtle. But well, there it is. You just have to, something is achievable if and only if it lies in the core of this game. Okay. So here are some other kind of remarkable properties of this W, which is that I've told you that WB is an integer, but in addition, W is convex. It's a convex game. And what does convexity mean? That if I look at some school dk, then the marginal increase in the valuation and the worth of the coalition that you get by adding dk to some subset of schools B2 is actually greater than when I add dk to a subset of B2. So suppose B1 is a subset of B2 and dk belongs to neither B1 or B2. Then, and suppose I consider what happens to the increase to the increase in valuations as I add this dk to both B2 and B1, then I have a greater increase when I add it to the larger coalition, right? So it's a increasing marginal contributions. Okay, and this is all I'm obtaining it from the network, right? So it's again a consequence of the max flow min cut theorem. Okay, so we have obtained a game W, which is and I'm able to say that a flow is feasible and a post transfer deficit vector is feasible if and only if it lies in the core. Moreover, that game is a convex game, and it's the value for every coalition in that game is an integer. Okay, so now what we want to do now think of a completely different problem. What we're trying to do is that we are trying to find an allocation in this cooperative game which is as equal as possible. Okay, we want to find an allocation in the cooperative game, right? We are trying to find an allocation. We're trying to distribute W of n as equally as possible, Okay, now what is the most what is one's immediate reaction? One's immediate reaction is, well, divide Wn equally amongst all players, Wn by n. But what's the problem here? Well, it may violate a core constraint. Okay, it may violate one of these core constraints. So if you divide equally, then you may end up not being in the core. Okay, and so for instance, in our examples, we said WD was 30. And so if you divided it equally, 30 by 7 is 4.28. But if you look at the coalition D3, D4, D5, then the worth of that coalition, W of this D2 is 13. So if you give, if you give 4.28 to these three guys, then you will get something which is 12.84, which is strictly less than 13. So in other words, these guys will block it. Okay. So what you have to do is to find an allocation in the core of this game W, which is as equal as possible. So that's our objective, and that's what this algorithm is going to do. Okay, so let me give you a more informal description of the algorithm. So in step I, we have these sets Z1 to Z minus I, which are subsets, disjoint subsets of the set of deficit schools. Now, given this, we are trying to find the set Zi, another set of schools. And how do we do it? We look at all deficit schools which are not in Z1 to Z minus I. We look at all subsets. We look at how much value these schools add to W of Z1 union to Z minus 1, how much extra value you get by adding this set of schools, and dividing that by the by the number of schools that you are adding. So the algorithm picks the subset Zi from the remaining deficit schools D minus this, which that has the highest marginal contribution to the set B minus I. So I don't know how clear that was, but so the algorithm inductively constructs a sequence of sets B naught BP and Z1 to ZP, which are subsets of deficit schools. So initially B naught is null. So we then look for all subsets of deficit schools and look at their look at what happens when you divide this value by the number of coalitions. So by the number of schools in that coalition. So if we take a set, let's say D of the set of subset of the set of schools, then WD minus W, the null set, that's 0. So it's WD over the cardinality of D. So you pick the D which has the highest average marginal contribution, and that's the first set of deficit schools you identify. Then having done so, you keep repeating this process, eliminating this set of schools that I have already chosen. Then from the remaining schools, you pick the greatest or the largest or the subset of remaining schools which have the highest average marginal contribution to the schools that you've already picked. Okay, and by this procedure, let's H star be the vector where all members of Zi share WZI equally, right? So this is the value that you obtain by using this procedure. Okay, so here we go around doing that. It's actually very simple. So in step 1, we look at WB over B when you're adding singletons, that's 4. When you're adding 2, it's 4. But turns out that when you add, it's highest when you take the set of schools D1 to D5, where you get 4.4, which is greater than all the other numbers. So you pick that and then you go again. So the partition that it generates is Z1 equal to D1, D2, D5, and W of Z1 is 22. So all these schools share equally. So you get 4.4, and step 2 chooses Z2 equal to D6, D7. You can and so the post-transfer deficit H star that you can get from this is 4.4 all the way up to the last 2 where you get 4. Okay, so this is the deficit post-transfer deficit vectors when you allow for all flows, not just integer flows, but for all flows, right? So as you can see, you are not getting integer flows here. And why are you not getting integer flows? Because although all these numbers are some W of Zi divided by the cardinality of Zi. We have shown that W of Zi must be, for any coalition or any subset of schools, W of Zi is an integer and Zi is an integer. But when you divide 2 integers, sadly, you do not always get an integer. So that is why you get 4.4, 4.4, etc. Now, so this is not the point is that this is not a legitimate post-transfer deficit vector, because we are not transferring teachers, because we are, fractional transfers are these post-transfer deficits can occur only if you permit fractional transfers, which we are not. Okay, So following Datta and Ray and Megiddo, we have the following result. The vector H star satisfies the following property. H star is achievable in gamma R. So H star is the vector of 4.4 for 5 guys and 4 for the last 2 guys. This is achievable. In other words, there exists a network flow which will generate this H star. And forget about 2, but 3 says it Lorenz dominates all achievable vectors in gamma R. Okay, so it Lorenz dominates all other achievable vectors in this. So this point in the core of this convex game is achievable, and it Lorenz dominates all other achievable vectors. So to the fact that it lies in the core relies heavily on the convexity of W. So there, we know the famous results of Shapley for convex games. We know that the marginal contribution vector for any arbitrary sequence or permutation of the players generates a core vector for a convex game. And moreover, there are the extreme points of that polytope, which forms the core. Okay. And now when you do this, when you follow this algorithm, it turns out that you are still in the core, and you can prove it quite easily using, Shapley's ideas. And you can show that it actually majorizes every other point or every other core allocation, right? But the problem, as I said, is that we are ending up with post-transfer deficits which are not achievable by integer flows. So we are only half done here. And so we now have to perform some kind of approximation or rounding, as it's called. Okay. So, no, can the flow F star that generates H star be a solution to our problem? Answer no, because H star may not be integral. And the important thing is that, why don't we just round it? It's not an integer, but let's round it to the nearest integer. But the problem is that rounding it arbitrarily will not work. In particular, if you do so, then you might violate those core constraints. Those core constraints or Megiddo constraints, you will end up violating. So in fact, in our example, you can show that in our example, that if you do so, then if you do it without care, then you will end up violating a core constraint. So then we know that that is not achievable. That's not in the core, and hence it's not achievable. Okay, so so what do we do? So what we do is that we find an achievable rounding vector by constructing another network, and what we call an auxiliary network, where we change the network. And we consider the original network G, which, if you recall, the sync nodes were D1 to D3 up to D7. And we augment it by 2 other sync nodes, Z1 and Z2, which you obtain from the solution to the integer, to the relaxed flow problem. So from the relaxed flow problem, we know that D1 through D5 are lumped together, right? So now we have an edge from from each of these deficit schools, D1 to D5, to one source node, to one sync node Z1, and similarly D6 and D7 are now connected to this node Z2. And what we do is that we make the capacity of we define the node capacities of Z1 and Z2 in a particular way, and we also put restrictions, integer restrictions on the capacity of each of these nodes D1 to S1, D2 to S2, D2 to Z1, etc., etc. And in this case, it turns out that they are between 0 and 1. And okay, so here in the example is how we compute the capacities of Z1 and Z2 and so on and so forth, and all these edges. And then what we do is the following, that we we construct this new network G prime by perturbing the existing network G using the partition Z1 to ZP, which we have obtained from the relaxed flow problem, and the vector H star, which we have also obtained from the relaxed flow problem. And then we create this new network and flow problem, where all capacities in this new problem are integral. And so by the integrality theorem, the max flow here must also be integral, right? So because again of the max flow min cut theorem, the max flow must be integral. And what we what is the proof? What we do is that we argue that this this flow that we have constructed is achievable in gamma r, and it generates an integral post-transfer vector h hat that Lorenz all other post-transfer deficit vectors achievable in gamma I. So this new rounding gives you an achievable flow in the relaxed problem, and those constraints must be satisfied in the integer problem as well. And then it generates an integral post-transfer deficit by virtue of this integrality theorem for the max flow in a network. And then the work consists in showing that it actually will Lorenz dominate all other post-transfer vectors achievable in the integer flow problem, right? So what we have, therefore, is something which Lorenz dominates other, which Lorenz dominates all other post-transfer deficit vectors in the integer problem. In other words, in the way that we want it to. Okay, so that is, how we prove our result. Essentially, we formulate it as a network flow problem. Then we, then using some existing results, we transform it into a problem of finding an allocation in the core of a cooperative game. Then we show that this game is convex, hence there exists an allocation which is Lorenz dominates all other core allocations. And then the final step of the proof is actually to show that this allocation is not necessarily achievable by an integer flow, but we can round it in a way such that it actually dominates, Lorenz dominates all other integer flows. Okay, so this is again just saying the same thing once again. Okay, so now let's talk about in sort of remaining 5-10 minutes, let me talk about strategy proofness. Okay. So here, we make some, I mean, this is our model. So imagine that every teacher TI has trichotomous preferences over school. The first indifference class consists of deficit schools in deficit schools in the in A of TI. So these are the acceptable schools, not including your owner school, the school of your initial assignment. And the second indifference class consists of um, the second indifference class consists of your owner school, and the third indifference class consists of non-acceptable deficit schools. So the assumption is that each TI is indifferent between acceptable deficit schools in A of TI, strictly prefers being transferred to a school in ATI, then remaining in her initial assignment, and her initial assignment is strictly preferred to any school in D minus A of TI. And what's the model here? So beta, alpha, and the initial assignment of teachers are publicly observable. But what is private information is your set A of TI. What are your acceptable schools? Only TI knows, and TI will reveal that. And we have a constructive procedure, and technically a sort of computer or somebody can actually figure out what where people ought to be transferred. And these are based on the announcements of acceptable sets. And let's say A is an n-tuple of acceptable sets, and every profile defines a TT problem gamma A, right? So this is just the problem defined by the announced acceptable sets. And a teacher transfer function TTF is a map that associates a Lorenz-dominant transfer policy in gamma A for every profile A. And so that's the point. Can we select a transfer such that all teachers have the proper incentive, have the correct incentives to report their true acceptable set? And so a TTF is manipulable by if a teacher is better off by misrepresenting her acceptable set. And it is strategy proof if no teacher can manipulate. All standard definitions. So proposition, there exists a strategy proof TTF, right? So in other words, yeah, so what we are saying is that, okay, you announce your acceptable set. We know that there exists a Lorenz optimal post-transfer deficit, which can be achieved by some transfer. We're going to find a way to pick such a transfer policy such that you cannot do better by misrepresenting your acceptable sets, right? No matter what you think the other acceptable sets are going to be. And we sort of use a choice function approach to this, and if something satisfies contraction consistency, essentially if you can rationalize it by means of an ordering, then it's good enough. Okay, so I'm almost done, so here are other things that we were thinking of doing. So allow teachers from surplus schools to move to both deficit and surplus schools. Schools cannot change status and compare deficit vectors. So this actually changes the graph in the original network, and we need to add what are called backward edges. Each teacher TI, backward edge TI to SJ, where SJ is a surplus school that she finds acceptable. So you can now have an acceptable school, which is also a surplus school. And the point is that the original result goes through pretty much in the same way, because essentially the properties of the cooperative game W still remain as before. The qualitative properties, in other words, it's convex, it's integer valued for any coalition, and feasibility remains the same, that it is now, the game is different, but something is feasible if and only if it belongs to the core. So those properties remain unchanged. So therefore, we can run our analysis through once again without any this thing. So yeah, you can have more versions of this. So yeah, so these are some things which we hope to do at some stage, but I really don't have much to say. Yeah. So thank you. If you guys, comments are very welcome, and
Thank you. Thank you
yeah.
very much, Arunava. It's
Thank you.
very interesting work. You see, it's the first time, I don't know, you know this literature much better, this sequential proof of non-manipulability and optimality of these transfers through really very rather, you see, very advanced mechanisms. You see, game theory, this Ford-Fulkerson theorem, etc. Great. Has it been published already?
No, we are still in the process of writing a final draft of the paper. So, trying to do some of the additions here and stuff like that. Maybe we need some more examples and stuff, but these examples are not that easy to construct. So we are struggling a little bit.
I can imagine. By the way, if you wish, we have this working paper series with very. I will send you the reference. If you wish, we can publish first version, some first version there. It's again up to you. Okay, please, questions.
Okay.
Comments, questions, remarks, whatever. Then let me start. My question is the following, you see, as far as I understand, you see your use of Ford-Fulkerson theorem in this very case, is it not possible to not to use it, but rather to go to this very sequential, let's say, distribution like in classic models? Sorry, maybe it's a naive question, but it is like a bridge, you see, in my mind between these models, and that's interesting. Yeah, please.
Okay, so I mean, I see what you're trying to say, Fuad. So, so what you're saying is, is there, or let me interpret your question in that way, is there something like some deferred acceptance algorithm kind of thing? Okay, you get transferred there, you get transferred somewhere else, etc., etc.
Absolutely.
I don't think that is really possible. I mean, I don't know. Maybe I could be wrong, but there are no direct ways of doing it. So I mean, I don't think that to say you could say that our paper is an existence result. So I would disagree with that in the sense that we are providing a construction, right? We have a network. You define, we extract from it a cooperative game. We are going to find, going to find a core, an allocation in the core, and then we're of that game, and then we're going to round it. Okay. Now this is a highly indirect way of doing it, but nevertheless, it is a constructive, proposal.
No, this I understand.
If you ask,
I don't know. My question is not critique. My question is has a different, let's say, reason. It's not critique at all. You see, it's a great work, absolutely. But
no.
Since it is indirect construction, I thought that maybe classic algorithm might be adjusted in some way to So
Okay, no, I didn't mean criticism in that sense, but I wasn't interpreting it as criticism in that sense. But I mean, it's a legitimate query that, um, is there some more direct way of doing it? I would say that I mean, we can't find something, and I would be surprised, quite honestly, because it would mean that several other classical problems in networks and so on have very simple solutions, and I'm not sure that you can find simple ways simple ways to do better than Ford Fulkerson or something like that. I mean, I don't know. I'm not a great expert in that area, so I shouldn't comment on it. I will admit that I'm. I mean, again, I'm not an expert in computational complexity, but I would conjecture that our mechanism is not computationally easy because we are finding uh, we are finding this solving some sort of max flow problem for every subset of schools.
yeah.
And whenever you start talking about every subset, then things sort of explode. So I would say that criticism is probably valid, that that although we have something which is constructive, the methods might be computationally difficult or something,
I understood that that was, in fact, the reason of my question, that computation is a method. It is a constructive proof, you see. You give a construction of how to do it. But
yes,
the construction might be rather difficult, and that is why I thought that
absolutely.
maybe there is some sequential procedure to
I
maybe to
understand exactly. I
invent
understand
some
exactly what you're trying
sequential
to say.
procedure, yeah.
I
Of this
understand
kind.
exactly what you're trying to say. And actually, the algorithm is a bit sequential,
Mhm.
right? The algorithm is a bit sequential. You are finding subsets of schools. Initially, you're trying to equalize as much as possible. Let's be very informal here. You're trying to equalize deficits across schools. So we find certain subsets of schools, and we are able to equalize amongst those schools without violating feasibility. Then, having done so, we find another subset of schools and we equalize there, right? So this is essentially what we are doing, right?
Yeah.
But the way that you select these subsets and so on depends on the underlying on the underlying network and the cooperative game that you construct from it and so on. So it's not, I mean, the sequential procedure, I know exactly the sort of thing that you may have in mind. Suppose there are two teachers who can be transferred. One guy would like to go to either of two schools, and one guy only wants to go to one of those schools. So the guy who has more restricted preferences, you ask him, okay, you go. Then
Yeah.
the other guy goes to the other one or something like that, right? So you might want to do something like that. But I mean, generalizing it to arbitrary numbers of teachers, schools with the supply constraints as well, because not you have to choose, for instance, which teachers that you want to be transferred. There may be a surplus school which has a surplus of 5, but 100 teachers want to leave that school. So which 5 will you choose? Is one of the problems you have to construct. And somehow this general way of constructing thing is able to deal with all of that.
And great part of the story is that finally you come to the proof that it's non-manipulable mechanism. It's
Well, this
great.
well, it's not. This part is not that this thing. I mean, it's just essentially it is just some fixed tie-breaking way of doing it.
Yeah,
And
I understand, but still you see rather complicated procedure, and finally comes to the
but but
non-manipulability.
but also remember, Fuad, that that preferences are very simple. If you
Yes.
have multiple alternative, I mean, if you say this is my best, my second best, third best, etc., then I make no claims about strategy proofness or anything like that, right? So here, because you have a lot of indifference, you're allowed to do things, but um, Yeah, yeah, I mean, in fact, yeah, it's essentially relies on some fixed tie-breaking rules and so on. So
Another story is that, as I said, that if you allow how that I can work in two schools,
yes,
for instance, one day here, half a day there, and these are my preferences, this situation might be really changed, and
yeah, So,
the result might be interesting also.
well, I mean, in this case, only the first part of the theorem applies, and you will do better because you don't have to do any rounding, and so you can have fractional matching and fractional flows and stuff like that. So yeah. So just another general point. I mean, it's not a particularly deep point or something, but it might be um, just a point worth noting that uh, this is a flow problem. You're trying to transfer things from there. Usually, the matching problem, it's there is some circularity and stuff like that. We are exchanging endowments and stuff like that. So the nature of the problem here is perhaps a little different.
Yeah,
So
it
for
is
instance,
switching to, it is
so the
switching to
SCOOM
another.
paper, is a problem which also looks at teacher transfer problems in France, but you can essentially only if one school sends a teacher out, then it must also receive a teacher in. Okay, so you're not allowed to change the balance, and therefore you can see immediately you have a more conventional matching problem, a top trading cycle type of thing where you have to adjust stuff and all that. So that's that paper. So our paper is perhaps a little different in the sense that we are actually wanting to push people from the source to certain things. And so perhaps there it's slightly different from the more conventional matching problems that we study. Okay, and yeah, okay.
And I think that it might have a lot of sorry, a lot of applications.
I don't know.
Yeah. Okay. Some other questions, comments, remarks, etc.
Just a small question.
I am it. Yeah.
Very interesting, Arunava. Very small question. One might consider just relaxing the restriction that no surplus school becomes a deficit school, but keep
Yes.
restriction on the other side. I guess your results would not change mathematically. Would that be?
Well, actually,
Would that be your guess?
well, I mean, Amit, I think in some ways it makes the problem easier because then you don't have to consider surplus schools at all. You just have teachers, and you have schools, and then you have a more conventional matching problem.
I see.
Right?
Yeah.
So you just look at the final deficit vector that is obtainable, or something like that, where I don't care, I can transfer, I can make a surplus school into a massive deficit school, but still somehow the overall deficit vector, the overall vector, which includes both surplus and deficit schools, is now better than it was before. So, I mean, although we haven't really studied that problem in very carefully, our initial instinct is that it actually makes the problem easier. So because here we have more constraints and stuff like that. So yeah, but it's a perfect valid comment that why do we care?
Well, I understand politically it would be difficult to
it's like an individual rationality.
What's in the position of a surplus school? I understand that, but at the same time, on the other side, you have the preferences of the teachers. And
Yes. I totally agree with you there. I mean, as far as the central planner is concerned, he or she does not really care about the initial classification, but a surplus school who would resist its teachers being transferred out and becoming a deficit. So you can think of that condition of not allowing surplus to slip into deficit as being a sort of individual rationality on surplus schools.
yes, I understand. But you're saying that mathematically, that's what makes it challenging.
I think it makes it harder. I mean, I wouldn't, bet a lot of money on it, but I think my initial reaction is that it actually makes it easier because you have fewer constraints to deal with. Perhaps you can solve the same. I mean, you have to redefine I'm being very loose here because now you have to define a different network and so on. But at some level, it seems to be an easier problem. But I should be more careful about this. But it's a perfectly valid observation. Why not allow all changes? There are various intermediate stages. I mean, intermediate models. I mean, the one that we can allow for immediately without too much change to our model is that you allow teachers from surplus schools to go to other surplus schools, provided that you don't upset a surplus school. You don't make it a deficit school. For instance, there are many people from a surplus school who want to leave and are valuable in other schools, but there are some other surplus schools where teachers can be transferred to this surplus school so that these other people can leave. So you can see easily that you can do better by allowing more transfers. And in this case, I think the model is pretty much unchanged. You have these backward flows, but these Megiddo type results go through. And so everything, once you have this game W, everything, and it has the same properties, we are okay. So that part can be handled very easily. And the other one, we conjecture, can be handled quite easily, but we have to think a little.
Thank you.
Okay, thank you very much. And some other questions, comments, remarks? No. Then we interrupt now until 12 Moscow time. And
I have one question, Fuad.
Yes,
how
please.
do I listen to Ahmed's talk? Will the same thing work with the same link?
Yes, absolutely the same link. Yes.
Okay, and that's in about 50 minutes from now, or? Yeah, okay.
Yeah, something 40 minutes from now, and then Ahmed will start, okay?
Okay. Thank you.
See you in 40 minutes. Bye-bye.
Okay, bye.
Даня, вы здесь?
Да, Фотогич, я здесь.
Да, Дань, значит, мы тогда не выключаем это и через 40 минут опять включаем.
Да, я могу запись саму остановить пока, чтобы...
Да, запись пока остановить, конечно. Again, another my good friend of mine, Ahmed Alkan, will give us a talk. Ahmed is working, is one of the leading scientists in Turkey, and I learn about these matchings from his lectures. I visited his lectures. I don't remember, it was 1995, 1996, something like that. And I know these models from his lecture, and I can say that he is one of the leading scientists in Turkey, member of Turkish Academy of Sciences, and professor of Sabancı University. But we were working in Bosphorus University for several years. Okay, Ahmed, floor is yours.
Thank you, Fuad. And thank you very much for the invitation. It's
Have
really
you heard what I said?
Can I be heard?
Switch on your microphone. Microphone is switched off.
Фуатагич, вы нас слышите?
Can I be heard? No?
У нас два компьютера и один...
I can hear you.
Микрофон.
I can hear you.
Arunava can hear me. Yes. Fuat can
Микрофон
hear you.
выключен.
Yes.
Фуатагич, мы с моего компьютера.
Там два разных компьютера, один для видео, другой для микрофона.
Фуатагич, для удобства просто так сделано. Главное, что вы слышите.
But this is not working.
Wait a bit.
Окей.
Непонятно.
Okay. I guess everything is okay. I can start gabbling. Thank you. Thank you for the invitation, dear Fuad. It's really a pleasure to be here. And as I said, as I was saying, this is a talk, not a paper at this point.
Даня, у Ахмета микрофон выключен, показывает.
There's a problem?
И делаем, что нет. Но мы его не слышим.
Не, все пишут, что слышно.
Is there a
А я
problem?
не слышу. Ну ладно.
Фуатагич, попробуйте еще раз, посмотрите. Может, звук может быть выключен, может быть, вы звук выключили на компьютере.
Да, извините, да, я разговаривал, да, все, теперь да. Ага.
Попробуйте. Фуатагич, вы нас...
Все, слышно. Sorry, it was my fault.
Okay. So,
sorry, I introduced you. Have you heard my introduction or not?
yes, I have.
Okay. So
Yes, thank you.
Go ahead.
Thank you for your kind words, and thank you for the invitation. The title of the talk is the revealed preference lattice and the lattice of stable matchings. I'm essentially going to be talking about two theorems, and I intend to more than sketch the proof of these two theorems, because I think there are a few steps in the proofs, and I like these proofs, and I think they are transparent. They make the stuff transparent. The material is about 25 years old, these two theorems. The reason I've been thinking about them now are several, and I think I will defer them sort of to the end of the presentation of these two theorems. Okay, so in fact, the motivation has to do with why I'm doing this, redoing this, has to do with representation of an individual or an agent. In this case, in a many-to-many matching market, okay? So and there will be two parts. Theorem one is about the individual. It's the theory of the individual, and it will simply be, and the individual will be represented by a choice function, and then I will show that there's a revealed preference representation of that individual. Afterwards, I will consider a market, a many-to-many matching market, where the agents are described by such choice functions or revealed preference lattices. But let me say a few words before I start. Fuad mentioned 95, 30 years ago. So will I. I started, we were teaching stable matching in courses. That's Gail Shapley. And actually, you know, as we all do, we look for meaningful applications in real life, which we can then bring to our modeling efforts. My mind was working in that direction. In Turkey, there is as in many other places, university placement is done by a central institution, and nationwide, from high school to university placement, students take a single exam, but with several parts. And so they have scores, and universities rank them according to these scores. Depending on the combination, there are 3 or 4 ways of obtaining a ranking over all students. So that's one side of the market, is the preferences of the universities are done by these exam scores. And on the other side, the students submit at a certain date their preference orderings over universities. And then this is standard. Then the computer finds the Gail Shapley algorithm, the optimal, it turns out to be university optimal matching, stable matching, and that's enforced. That's the end of the story. But it comes in waves, but there are frequently there are complaints about the fact that education, especially in high school, is reduced to preparing for these centralized exams. And I have personally joined in these complaints that it's spoiling the secondary education. So one wonders what can be done about it. This is being talked about for 30, 40 years, but there has been no possible departure from the current system, in spite of the complaints, for good reasons. The particular idea passed through my mind. It was a crazy idea, but whether this procedure can be done in 2 stages, whether in the first stage, in a centralized way, using exactly the same exam scores and student preferences, whether the center could find let me call it an interview schedule. In other words, send to each department, college, more than its quota of students, maybe twice or 3 times, whatever, that's not so important. And then the department may use a certain duration, say a month or so, getting in touch with those students which have been specified by the center, getting to know those students in a deeper way, perhaps through their own particular exams, or even possibly interviews, etc. And the idea was that maybe if this were done, then the universities could monitor the quality of education in the high schools, so that instead of just these multiple choice exams where the student's attention is reduced to only a couple of minutes, can be utilized in a deeper way, and secondary education could be more creative. But I gave up on the idea, although it revisits me. I'm mentioning this because, personal anecdote, this is how I started, I think it was 96, 97, thinking about many-to-many matching, okay? College admissions, university admissions, that's many-to-one matching, and it's covered in the 1962 Gale-Shapley model. But if one finds an interview schedule the way I described, that's the first stage of a mechanism. There, each student is being, not only each college is being sent more than its quota of students, but each student is being sent to more than one college in the first stage of this mechanism. And the idea was that after the universities correct their imperfect information on the student in this manner, there can be a resubmission of their preference orderings to the center. That was the idea. I am mentioning this, it's just a personal anecdote, describing how I got into, how I started thinking about many-to-many matching. And so I was checking whether mathematically the basic theorems would continue to hold in such in a many-to-many matching market. And except for strategy proofness, it turns out as long as you have so-called responsive preferences, in other words, if the preferences of each agent is based on a linear order, then everything goes through. Deferred acceptance algorithm works just as before, and also in particular the lattice structure of the set of stable matchings. Okay, so I gave up on this interviewing idea for two reasons. One is that I'm interested, but it turns out to be a very difficult question mathematically to capture. And the second reason is simply corruption, that if colleges have the authority to interview their students, then they will be doing that in unwanted ways. Okay, so I gave up on that idea, but I realized that the responsive preferences for many-to-many matching markets is simply too restrictive, and started thinking about, as have been done by many other matching theorists, less restricted preferences under which the basic theorems in stable matching theory would continue to hold. Okay. So as Fuad mentioned, this is the second half of the 90s, and Professor Aleskarov is with us at Boğaziçi University, and he's a role model for using time to work. And early in the morning, the students are visiting his office. He was giving a course on choice theory, on choice functions. So I learned a lot from him and also from his students. We were sharing students. Then, so the time was opportune to consider thinking of a matching market where each agent is described by a choice function. Okay, so a choice function is a function defined on a universal set such that for any element of the power set for any subset of the universal set. What is chosen is contained in the choice set. So we have choice set and chosen, choice sets and chosen sets. Okay. Now, recently, there is a choice function literature in Economics 501, introductory economics courses go through, where the chosen set is interpreted as consisting of alternatives, meaning that essentially the individual is indifferent between the elements in the chosen set. This is entirely, this is by no means the case here. And in fact, these choice functions have been, are being referred to as combinatorial choice functions. So I'd like to emphasize that. The universal set consists of elements which are not alternatives, okay? Really, they are, and the chosen set is, one should think of a chosen set as a team that the individual is trying to come up with. So diversity, for example, if on one side we might have research directors on one side of the, if it's a market, or in this case, the individual may be a research director, and the universal set may consist of researchers, macroeconomists, microeconomists, econometricians, behavioral economic specialists, even neuroscientists, etc., etc. So the idea is to come up with a team, and you need the individuals in a certain combination, and they are not alternatives to each other. So this immediately forbids the idea of having a preference ordering, a linear order over the elements of the universal set. Okay. So we'll focus on the image of a choice function, of the choice function, and regard it as the consumption set of the individual. Okay. Let me mention something that I will repeat after the presentation of these two theorems I do. That is, in economics, in economic theory, it's standard that one describes an individual, an agent, by a preference ordering on the consumption set. And then sometimes we employ the choice function that is compatible, that derives from these preference orderings. It is an important, or the important point of this talk, that I'm reversing that here. So the choice function is the primitive description of the individual, and observing the choices made by these, that this choice function comprises, we get what's called the revealed preference binary relation on the consumption set. Okay, that's simply defined as a chosen set S is revealed better than another chosen set S prime if and only if what the individual chooses from their union, from the union of the elements in both S and S prime, if the chosen set is S. Okay. So we would say that S prime could have been chosen, wasn't chosen, S is chosen, so S is revealed better than S prime. Okay, so this is, of course, neither S nor S prime need be chosen given an arbitrary pair, so this relation is incomplete. Okay. Now, a property, well-known property of a choice function is path independence. Simply that if I operate the choice function on the union of two choice sets, T and T prime, I may do this in a different order. First, employ the choice function on one of the sets, just put aside the unchosen elements, unite it with the other one and continue, and the result would not change. That's the definition of path independence. Okay, I should speed up. These definitions are well known. So a particular property is called substitutability. So this choice function satisfies substitutability if I make a certain choice from a set and that set shrinks, and if an element is a chosen set, it is a chosen element from the original set, but still in the choice set after the shrinkage, that element would still be chosen. Well-known usage, substitutability. The other axiom, the other property, I have been calling this consistency. It is used, referred to by different names, and that is given a set, a choice from a certain set, and consider a shrinkage, but such that what is chosen from the first choice set is entirely contained in the set after the shrinkage, that the chosen set should not change. Okay, so this path independence property is equivalent to substitutability and what I've called consistency. That's Eiserman, Malishevsky, and this is well known. And what I learned going back to about 30 years ago, starting with my friendship with Fuad. Okay. Oh, I'm missing. Can we call that? What? There are some pages that I'm missing here. What happened?
This presentation, which is unnecessary. 1 second. This presentation is Anna sent me and says that it is the full version. Сейчас я ее найду. 1 second.
Daniel, can I use the...
Yes, laptop, yes, of course.
But there are some important pages missing here.
1 second. I don't know why. I tried to call the in. So you can write. You would like...
Wait. Are there these pages in other computer? Ahmed,
Yes.
are these pages in your other computer?
You know, we had prepared the slides, but I think there are some pages missing from the slides. So let me
Okay. Okay.
let me
then you-
continue.
Okay.
Remember, I said I have two theorems to talk about. Pages on the slides pertaining to the first theorem is missing what we have uploaded. So I will try to use the screen to
Okay.
proceed.
Yes.
Okay?
Yes.
So this
You can just write right here. Yeah, yeah, of course, you can write.
okay. So can you help me when as I proceed? Oh,
Uh-huh.
oh, this is going to be difficult. How do I erase?
Maybe try to with my mouse.
Huh?
Maybe try to use the mouse.
Erase. I should be able to
Ah.
write and erase.
Yes.
But
Yes.
Would you like to write theorem?
here?
Yes, yes. And choose. whatever.
Okay. And I write here.
Yes, here.
So this writes here, but okay. I'm sorry for this, but I will. Okay. Theorem. Okay. No.
Do it here. I guess it is better to do here. Let's try to. No. Here. Yes, yes, try.
No, but this is not going to work. Okay.
Maybe it is better to use the mouse.
This was not a good idea. Here the
Or
eraser.
can you write the text by the keyboard? Can you do it by using this?
Can we erase this?
Of course. 1 second. Let's try to. Okay. Okay. Try to write.
Where? Oh, I should have stayed in the other room. Reveal preference. I'm sorry
I
for
know.
this. Maybe I will.
I know what we can do. We can use the whiteboard. 1 second.
Okay. I can be heard.
Yes, yes,
Yes.
yes.
Okay. And this is visible.
Yes, yes.
Okay. Thank you. So I'm sorry for this interruption, but for the second theorem, the slides are okay, but not for this one. Can you see me? Yes?
Yes.
Yes.
Okay, sorry. So this is the first theorem I will talk about. Says that the revealed preference binary relation is a lattice if C is path independent. Okay. So proof.
Sorry.
How am I doing? Am I visible and being heard?
Yeah, it's good, Amit.
Yes.
It's good. Yeah, yeah.
Okay. So this is the old style. It's better I have to recall the steps. The first one is that is a partial order under path independence, because the important property is transitivity. You know, if S1 is better than S2, and if S2 is better than S3, let's say, then I want to show that if I choose from S1 and S3, I would get S1, right? So from these, I should get S1 if I choose from the union of S1 and S3, but this is by path independence equal to, because S1 is better than S2, okay? Then again, by path independence, okay, just continue. Now use the fact that S2 is better than S3. So the choice is between S1 and S2, and that gives me S1 using the fact that S1 is better than S2. Daniel, can I use this smoothly to erase?
Yes, of course. Every
But there is this problem with
maybe I can help you.
sticky. Okay.
In one it is good.
So transitivity and reflexivity as asymmetricity is trivial under a partial order. There's no problem with that. Now, the
Maybe it's better to.
okay, so it's a partial order, and so if S1 and S2 take any two chosen sets, if they are not comparable, what is chosen from them is least upper bound under this relation. Proof, now call this S star, and if you take another chosen set, which is better than S1 and better than S2, okay, then so another chosen sets that's revealed better than S1 and better than S2 is okay, a star, that's the important element, which will emerge as the least upper bound under the revealed preference relation is, by definition, is what is chosen from the union of S1 and S2, and by path independence, this is I will get S double star, meaning that S double star is better than S star. So it's the least upper bound. S star is the least upper bound. Okay, so can I erase this now? These
I can
Yes,
delete
please. Okay. So at this point, this revealed preference relation, so simply defined, is under path independence. It's immediate that this is a semilattice. Every pair of elements has a least upper bound. By the way, we will use the notation S1 join S2 in this case. And so it's a semilattice. And since everything is finite here, we obtain that the revealed preference binary relation is a lattice. Okay, that's the end of the statement proof. But actually, the theorem continues importantly, where it says the join of two chosen sets is, as I just proved, what is chosen from their union, okay? But the next line is important. That is, what about the greatest lower bound, or the meet of two elements? Okay? And that turns out to be what is chosen from the intersection of two sets, S1 bar, S2 bar, where S1 bar is the largest superset of S1. So this is true for any element of the consumption set or a chosen set, such that what is chosen from S bar is S1 bar. Okay, so we'll refer to these sets as the closed set of S1. So let me summarize here what I'm asserting something in the theorem that this is the least upper bound of this lattice, the join element, and the greatest lower bound, or the meet, is found in this way. Namely, you for each element of the consumption set, there is a unique closed set defined in this way. How is this definition possible? You know, if take any S in the consumption set, okay? And So if T and T prime are two choice sets such that from these sets I choose S, then by path independence, from their union, I choose S, okay? So these are sets, choice sets, which give me S, and I can unite them, and I would still get S by path independence. So the union of all these sets is what I call S bar. It's unique. Anna, what happened to the first pages of it?
No, it's the final presentation.
It's not here. Do you have them?
Mm,
Okay. Now, but they are not here.
First of all, I just opened the presentation with Assembly. Is the errand that you're looking for?
Yes, it's here. Okay. So why didn't I find it previous? Okay, let me go back. One second. Okay. Thank you. I apologize for this interruption. Something happened in the slides. I couldn't find the page pertaining to the first theorem, but now we have recovered them. So I'm proving this theorem, which says that the revealed preference relation of a path-independent choice function on the consumption set, the image of C is a lattice where we have these formulas for the join and the meet. And the join is simply what is chosen from the union of two chosen sets if they are not comparable. Okay. So, and the meet, that's the interesting part, is the claim is that there is a unique largest superset of S as a choice set from which S is chosen. And if you take two elements of the consumption set, any two elements, S and S prime, find their closures, closed sets, take the intersection and choose, and that's going to be the meet of the of these two elements. Okay, so three more points, and then this proof will be over. Okay. This relationship is one-to-one. Okay. I had shown that. The next thing to see is that the intersection of two closed sets is a closed set because take any element outside the intersection of the closed sets. Then that element is without loss of generality, not in one of the closed sets, say S bar. That means that if I unite this element with S, then A would be chosen because it's not in the closure. By path independence, then A would be chosen by this should be an intersection. Okay, if I unite A with the intersection of these two closed sets, and so therefore any so by substitutability, the intersection is a closed set. Now this says that the collection of all closed sets in the power set is a lattice under the relation inclusion. Okay. And to complete the proof, we just have to see that this map between from the closed sets to the chosen sets, the consumption set, that relationship is 1-to-1. On the right-hand side, on the revealed preference relation, on the chosen sets, the chosen sets is a lattice. We just established that, okay, where we know the how to find the join of two elements. Here on the left-hand side, we have the closed sets is a lattice, and the greatest lower bound is simply the intersection of closed sets. So now we see that this relationship is order preserving, and what we have is a lattice isomorphism. The conclusion will be that if we operate the choice function on this should be an intersection, I'm sorry, the bottom line, what is chosen from the intersection of two closed sets is, because this relationship is order preserving, the greatest lower bound of the chosen sets. So that proves the theorem. Now, to see that the relationship is order preserving, take any two closed sets, one inside the other, then let's observe by path independence that if we make a choice from the union of S and S prime, then using this closed set relationship definitions, we will get that S prime is better than S. So one closed set inside the other, then the one that's inside its chosen set is the other one is preferred to the one that's inside. Okay, so there is isomorphism between the lattice of closed sets and the lattice of chosen sets, and which gives us this formula. Okay. Okay, I will now shift to theorem 2, the other theorem, which is going to be on the many-to-many matching market. But first, I would like to briefly recall the one-to-one matching. In that case, the lattice theorem says that the set of all stable matchings is a lattice, turns out to be distributive, under the group preferences. What happened to the definition there? Oh, these pages are confused. Okay. Sorry, let me read this.
Ahmed, sorry.
Yes.
The story is that this theorem says that there are distributive lattices, as far as I remember, when these individual preferences are linear orders, right? Full order over the for men over women and back. Right?
No, we are well beyond. We are putting aside linear orders.
No. I mean,
in the one-to-one matching market, we are back to linear orders, of course.
Yeah,
yes.
But this very theorem about the distributive lattice were in the case of linear orders.
Yes, in this case, let me take a few minutes. Okay, sorry for the first part. Now, theorem 1 said that if the choice function is path independent, then the revealed preference binary relation is a lattice, and I know everything about the lattice. Okay, this is a big domain, the domain of path independent choice functions, and in mechanism design, it's being used, but I think not fully utilized yet for design. It's beyond the responsive preference domain. The path-independent domain is very rich. And so the idea that I'm pursuing is that if I consider an individual defined by a choice function, then the revealed preference relation is a very nice order, a lattice, okay, where I know in particular, where I know how to find the greatest lower bound. As you will see, that's going to be important, of two elements. Now, let's take a brief look to recall and to observe some similarities about what I will be doing when I go to the matching market, many-to-many matching market, about the one-to-one market, okay? So the set of all stable matchings is a lattice under the group preferences of F firms or workers where the supremum, let's call it, the join or the supremum of two stable matchings under the group preferences of the firms is simply what each firm chooses between the two mates that it has under mu and mu prime, okay? And the infimum, or the meat of two stable matchings, is where each firm is matched with the less preferred one, okay? And this theorem also says that the firm supremum is identical with the worker infimum. Okay. Quickly, how is this proved? By the way, the proof of this theorem is attributed to Conway. I understand he just made this remark when he heard about this definition, the solution concept, set of stable matchings. He said, it's got to be a lattice. It's attributed to Conway, and the proof is extremely simple. Here is how I think about it. Say mu is a matching, this is one-to-one, right? Let's say it's done on Monday, and mu prime is a matching on Tuesday, and some firms have the same mate, same worker on Monday and on Tuesday, and some have two distinct mates. Invite them to a meeting on Wednesday and ask a firm to come in with his two mates to a hall, let's say a dining hall. And if the mate is identical, then put them on a table for two individuals. But if that firm invited to the dining hall has two distinct mates, let him be seated with each mate on one side, on each side, okay? And suppose the one on the right, he prefers to the one on the left. And it's immediately seen that the one on the right is got to be, so the one on the right, let's say, is the Tuesday matching mate, must have a mate, a firm on Monday. Why? Otherwise, if that worker is single on Monday, they would be blocking the Monday matching with our firm F. So then that firm is called on to sit by this mate. And then if you repeat this argument, you end up, because of finiteness, you get a cycle, a circle, where of firms and workers seated alternately, where everyone is, in fact, looking in the same direction in terms of preference. So said another way, is that in the one-to-one case, then you have the cycle decomposition, and in one cycle it may be that the firms are looking clockwise for their more preferred worker between the Monday and Tuesday matchings. In another table on the other direction. Well, the supremum matching is defined by putting together these cycles picked according to the preferences of the firms. Okay, so the observation is that when you ask each firm to point at the worker that he prefers between mu and mu prime, no two firms point at the same worker. And therefore, we end up with a matching, and that matching turns out to be stable. Okay. Now, I will move to many-to-many many-to-many matching and do exactly the same thing as in one-to-one matching. And if the choice functions are path independent and they have an additional, they satisfy an additional property called size monotonicity, then doing exactly the same thing gives us two matchings, which are respectively the undergroup preferences, the supremum for the firm side, and the infimum for the firm side. So let me go over them. Okay. But I think these slides we revised, but are these the final slides? No. Anyway, I have to make corrections. Is this the final edited one?
Yes, because you remember we included this parenthesis here.
Okay, so let me read. Now, let's take, by the way, size monotonicity is a choice function is size monotone if the number of elements chosen from a set is not greater than the number of elements chosen when the choice set expands. Okay. That is size monotonicity. And under this condition, there are typically many stable matchings, and they compose a lattice, which turns out to be distributive under the group preferences in the following way. What happens? I take these two matchings, mu prime, and for each firm, for each individual, I let that firm to choose from the union of the teams of the chosen sets that this firm has in these two matchings, okay? It's a generalization of what is done in the one-to-one matching. In the one-to-one matching, the firm chooses between the two individual workers that he prefers. Here, the firm has two teams, maybe distinct, or they may have a non-empty intersection. We are letting each firm, this firm, to choose from the union of these two teams, of these two chosen sets, okay? And that, we recall, under path independence, is the join in the revealed preference lattice of that firm, okay? This we call, when we do this for every firm, let us call the matching that we get in the end, this matching, a matching is any subset of F cross W, okay? We will get a subset of F cross W when we do this operation. We call that we will show that this is the least upper bound under F preferences for under group preferences of these two matchings. Now, line 2, the line 2 below, there is a misprint here. That is the meet, the infimum, the firm infimum of these two matchings will be what each firm chooses from the intersection of the closures of these two teams. Since there is a misprint, let me repeat them. We let each firm choose from the closed sets, from the closures, from the intersection of the closures of their two teams under mu in mu and mu prime. That we recall from theorem 1 is the meet in the revealed preference of that firm. Okay, so when we do this, the theorem says we will be getting the group preference infimum for the firm of the firm side. And in fact, so here for the firm side, we have defined the two matchings, one above, one below. We will show that these are stable, and the upper one called the supremum and the lower one, the infimum, they are defined in this manner. And we will show that at the same time as in one-to-one matching, the firm supremum is identical with the worker infimum. Okay. Now, let me go a little slow on this page. It's a very simple lemma here, and that plays a big role in the proof of this theorem. And I would like to make some comments. What does this say? This lemma says that the meet, this is theory of the individual. Take any individual with a path-independent choice function, okay? Not necessarily size monotone at this moment, at this point. Take any two chosen sets, S1, S2. Their meet contains the intersection of S1, one of these sets, and the closure of the second set. So S1 intersection closure of S2. Okay. So it's interesting that this meet has this property that is using, remember this lattice isomorphism, a chosen set and a closed set, the intersection of the meet has this property, okay? And the proof is very simple. It uses substitutability. Look, take the intersection of the closure of two chosen sets, S1 bar intersection S2 bar. Remember, this is when the individual chooses, what the individual chooses from the set is the meet of that, of this pair. That this is clearly contained in the closure of any one of these sets. And by definition, what is chosen from the closure of S1 is S1 itself. Now, by substitutability, so what we have is that in the first line, we have a set S1 bar, and then S1 bar intersection S2 bar is a shrinkage of that. So what is chosen from the initial set S1 bar intersection the shrink the set after the shrinkage, the intersection must be contained in what is chosen from the set after the shrinkage. And this is exactly what this lemma says. So it's very simple to prove this lemma, but it's going to play a very nice role in proving the theorem about the market, many-to-many matching market. Okay. Maybe I will speed up a little bit. So the proof has essentially 3 observations, 3 or 4. The first one says that the firm supremum is a subset of F cross W, is a matching, is necessarily contained in the worker infimum. Okay, how does one prove that? Take a pair, FW, that's in the firm supremum. If there are 2 cases, one is that this worker, this pair W, is either in the intersection of, remember, it's in firm supremum. So recall the firm supremum is we have allowed this firm to unite the workers that he has in these 2 matchings and choose from them. Okay. There are 2 possibilities. This worker is either in both mu and mu prime for this firm, matched with this firm. Then this firm, by definition, is in the intersection of the teams that the worker is matched with in mu and mu prime. Okay. The second possibility is that this worker may be matched with in mu, but not in mu prime. Okay. Now, by substitutability, F must like W at mu prime. So W is outside mu prime of F, but F must like W at prime, meaning that if W is joined with the team that F gets in under mu prime, W would be chosen. Why? Because F chose W from the union of mu of F and mu prime of F. So mu prime of F is a shrinkage. F would choose W from mu prime of F. And that, in words, we say F likes W at mu prime. Okay? So remember, mu prime is stable. Then it must be that W does not like F at mu prime. Prime is missing here. Because otherwise mu prime would be unstable. So this firm is an element of the closure of mu prime of W. There is a bar missing here. I think we have mismatched 2 different set of slides, and I'm showing you a set of slides that we later edited, but somehow are stuck with this one. To repeat, so the conclusion of this first part here is that F then must be in the closure of mu prime of W. F is not in mu prime of W, and W does not like F at mu prime, so F by definition is in the closure of mu prime of W. So connecting these 2 cases together, so F is in the intersection of mu of W and the closure of mu prime of W. Okay, so by Mead lemma, F is in the meet of mu of W and mu prime of W. Okay. sorry for the misprints. This says that the firm supremum is contained in the worker infimum. As it goes, we need another condition here. Size monotonicity enters, and then we get an equality that it must be that firm supremum is identical with the worker infimum. How does that work? Let's look at this bottom line, okay? From the first bullet, we see that the firm infimum must contain no more elements than the worker infimum, okay? That's the first inequality. It comes from the first bullet. Then the second inequality comes from size monotonicity. The worker infimum must contain no more elements than the worker supremum. That's size monotonicity. Then we use the first bullet again. The worker supremum contains no more elements than the firm infimum, and then once again size monotonicity. So we get this these four inequalities, and it must be that all these inequalities are equations, in fact, because in the beginning we have the firm infimum, and at the end we have the firm in the number of elements. So these inequalities must, in fact, be equalities. The conclusion is that the firm infimum is identical with the worker. The firm supremum is identical with the worker infimum. Okay. So what remains? What remains is to see the fact that these matchings are, in fact, stable. First, individually rational. So the firm supremum is individually rational, clear by the consistency property of the choice functions. For the firm side, clearly, but because of the fact that the firm infimum is identical with the worker, firm supremum is identical with the worker infimum, then also if we let the workers choose from the teams that they are matched with in the worker infimum, they should stay put. So that shows the fact that this matching is individually rational, not just for the firms, but also for the workers. Finally, to see the stability, let's see. Okay. We claim this firm supremum is stable. Why? Because take any element, any pair, FW, which is not in this matching, okay? Mu F, mu W. And suppose the firm likes W at this matching, would like to, would choose W when united with the workers that he has otherwise, okay? Now, by substitutability, this firm likes W at the original two matchings, mu and mu prime, okay? Okay, by substitutability, he would choose if he likes, if this firm likes W at the supremum of mu and mu prime, F would choose W at mu and at mu prime, okay? But these matchings are stable. So when we look at W, it must be that W does not like F at mu or at mu prime. That translates in our language to the fact that this firm is in the closure of mu of W, intersection mu prime of W. Okay. Now, we will see that simply that W does not like this firm at the firm supremum, because look at these two lines. If we unite F with what our worker small w gets at the worker infimum, when we substitute for the worker infimum, we get this expression on the right. Okay. But F is in the intersection. So we get the line, next line, and that is simply the worker infimum of W. Okay. So observation, our worker, if F is united with the team that this worker gets at the worker infimum, would not choose, has not chosen F, because FW is outside this matching. Okay. So that is that completes the proof. Yeah, I see that I have taken a lot of time. No,
it's okay.
Okay. Okay, so let me round up why I did this. I thought that I would be much smoother and much faster in presenting you with these two theorems. I would like to point out, I have taken a lot of time with them, that I discovered these two theorems quite some time ago, about 25 years ago, but they have been with me since for several reasons. One is that in the proof of theorem 1 is new. I did not see it that way 25 years ago. And this lattice isomorphism is almost immediate. And I find it this revealed preference lattice property under path independence is so transparent under this proof that I want as a first step to share it with you. Okay. Next, that using these revealed preference lattices and with the observation, this meat lemma, we get the fact that the set of stable matchings are in fact a lattice under group preferences. Okay, one can continue. There are some other properties, for example, the fact that every agent firm or worker has the same number of mates in every stable matching is an immediate corollary, and some other structural properties, and those just come very easily. So to repeat, these mathematical facts give us the results for many-to-many matching, undersized monotonicity in almost a parallel way as in one-to-one matching, just mimicking what is done in the case of one-to-one matching. And that I find impressive, and I wanted to share with you. The point, motivation was, go back to the beginning. Why am I currently, this is in the front of my mind? Because, you know, about 25 years later, I look at many papers in many-to-one or many-to-many matching. And there, as I commented when I started this talk initially, the individual is said to have a preference ordering over all chosen sets, or over all a collection of the power set of the universal set, okay? And then the observation is that in stable matching theory, the choice function suffices to get all these results. As long as the solution that we are using is stability, one doesn't need the full preference ordering at all, okay? The underpath independence, as we've seen, the revealed preference relation is a partial order, sure, incomplete, but the comparisons that are not there never get worked, one never needs the individual to consider those comparisons. So there is simply unnecessary information when you are starting with a preference ordering and then working with the choice function. I truly don't understand why this extra baggage is carried. Okay, so this is a simple motivation. To repeat, it is sufficient to describe an individual by a choice function and then work with the revealed preference lattice under path independence. As we've seen, it does quite a lot of work in simple ways. Recently, in fact, within the last year or two, I've come across attempts to find a utility function over the entire power set, maximization of which will give a choice function, path independent, plus size, monotone, whatever. And this, I find it a bit difficult to carry to its ultimate point for two reasons. First, I think my main point is that this is unnecessary because we have the this, revealed preference lattice does everything, at least in what we have looked at so far. But the preference relation should be on the consumption set and not on the entire power set. But certain reasons that is not done or doable, and the attempt is to come up with a utility function on the entire power set to recover the choice function. I understand, I am not an empirical economist, but I understand that this is done so as to facilitate empirical work in this setting, in the matching market setting. I have difficulty in going along with it. For one reason is that it's defined on this entire power set, and the utility function that one gets depends on whether you restrict it to not the entire power set, but to parts of the power set. So that's problematic, but also because this is a discrete setting, and the utility function on a discrete setting to rationalize a choice function, I have some difficulties in going through with it. So I'm simply wondering whether this discrete method can be continued further in finding further properties of this lattice, the revealed preference lattice, which will be helpful in making observations empirically instead of using a utility function, which I have, as I mentioned, I have problems with. Just to conclude, recently in a recent work, for example, on one-to-one matching, we used the rotations, the rotation poset that's associated with the stable matching lattice, and that rests on the Birkhoff representation theorem for distributive lattices, generates the entire lattice, and it's wonderful. You the stable matching lattice can be huge. The number of stable matchings could be increasing in a way that cannot be bounded by a polynomial, but this rotation poset, based on the, which is nothing but the poset described by the Birkhoff representation theorem, that rotation poset generates the entire lattice and gives us a lot of enables one to find many things, come up with algorithms that are polynomially bounded, even though stable matching itself is not. And there's a recent paper in mathematical programming that appeared in mathematical programming by Faenza and others that do the same thing, rotations using the Birkhoff based on the Birkhoff representation theorem for many-to-many matching. So, final two sentences: the revealed preference lattice under path independence is not distributive. I understand it's so-called meet distributive, but perhaps not as simple as the Birkhoff representation theorem, but akin to that. There might be, there are basic ways of capturing that lattice as in the Birkhoff representation theorem. So in my mind, maybe there is this avenue to be pursued that can also prove useful in empirical work. It's not my material. It's too far-fetched a claim, but I mentioned that looking for utility functions to rationalize discrete choice functions need to be clarified, I think. I think that's going to be the end of my talk.
Thank you very much, Ahmet. Thank you very much. Very interesting.
I'm sorry for, but we prepared slides, but somehow ended up with a previous copy, I think.
Never mind. You see, I can respond a bit to your questions. From my point of view, to make this utility representation for power set is not very interesting thing, because you see, utility as usual, you see, is attributed to the object, not to the set. But the way of generalization of it, I did it in the book, which is called Utility Functions, Choice and Preference. When I considered this evaluation with error, and error was dependent on the set where we consider this alternative. And that might work. On the other hand, I have a question. This very monotonicity which you used, and size monotonicity, if we apply just usual monotonicity in terms of subsets, will it not work? I mean, together with Python dependence.
Maybe I will ask you to repeat your question, but you have given me a chance. You have given me a chance to make an observation. Remember, I don't know if you remember, in the proof, we get these inequalities, cardinality inequalities, at each end of which we have the same matching, okay? And this size monotonicity condition does a lot and has proved very useful in many, many aspects, in particular getting, for example, strategy proofness in the many-to-one case. But it's to fix, to get the equality there in those inequalities, you just need size monotonicity, and that's how I discovered size monotonicity, by looking at this sequence of inequalities.
Okay, maybe we will talk about it in more detail. Let's do the following. If some other questions, please, maybe people might have a question. Please, questions, comments, remarks. No. So we have some time to interrupt now and meet again at 2:30 Moscow time, and Mario, it will be your turn. Okay? Thank you very much, Ahmet, and see you at 2:30. Bye-bye. So the next our speaker in our autumn school is Mario Gorachina from the Department of Economics and Law of University of Cassino and Southern Lazio, our good friend from Italy. And Mario is also, I'm very proud to say that he is also he's also working in a higher school of economics in Nizhny Novgorod in laboratory of algorithms and technologies for network analysis. And here we do some common work, because you see, I also work in this some new network analysis. Okay, Mario, not to spend time, please go ahead.
So first of all, let me thank for the opportunity to talk at this autumn school. At the beginning, I was a little bit worried about talking about some topics related to artificial intelligence within this autumn school on decision analysis. But then I realized that there are many studies that are somehow starting from the 90s of last century that try to merge those two topics, those two fields. So I am very sure that this could be of interest. I will give a general talk on how to represent problems using networks, and how to represent those networks in some vector space, in some vector spaces. So I will start from the very beginning. I will give also the basic definitions in case somebody is not aware of the possibility, but I think that everybody does, the possibility to represent problems, many problems using networks. And then little by little, I will give an historical perspective of this field, and also some recent results and possible research directions. So first of all, as I said, let me say what is a network. And a network, as we imagine, as we all probably know, is a collection of points that sometimes are called vertices, nodes, actors, or whatever, that are joined together in pairs by some lines that are usually called edges. And of course, there are several real-world problems that can be modeled as networks. The first that might come to our mind are, of course, internet, that is actually a network in which computers are connected in this fashion as a network, or also in human societies where a collection of people are linked by some social interactions. And networks are very interesting for several reasons. First of all, because they provide an universal language for describing complex data. So networks for science, nature, and technology are somehow more similar than one might expect. And also there is a shared vocabulary that we can use across different disciplines and fields. And due to also to the huge amount of data that is available and that somehow represent real-world problems in terms of modeled in terms of networks, it is also interesting to understand how we can analyze this huge amount of data. And the impact of those studies, of those methodologies for the analysis of networks has an impact, as I said, in many different disciplines. But one might ask why we should represent a problem using a network. This is usually due to the fact that when we use networks, we are able to capture the interactions that are existing among and between the different parts and actors that are actually the part of our problem. And the pattern of those connections might provide some insights related to the problem that are not clearly visible if we do not use network as a modeling technique. And for example, we know that some patterns that exist in social network affect the way in which people obtain information or form their opinions. And another example, in financially connected companies, for example, we might understand some causal behavior among different financial assets studying those interactions. So a first example of networks is, of course, social networks. We all know social networks, and in general, in those networks, the nodes are people, and the edges might represent a friendship existing between people, or the fact that one follows another person, like what happens in some social networks, or some people reply to some posts of some other, thus creating a connection an edge between two persons. Of course, there are many different types of interactions, and for example, we might have in those networks, it might happen that the connection is directed in the sense that, for example, I answer to a post of some person, and there are also, or I put a like to some post of some people, and there are also situations in which there are those loops. That means that the person somehow likes his posts or somehow has an interaction with itself. Social networks are also present in scientific literature. This is one of the first papers that came out on this topic, in which there is a representation of the co-authorship networks for co-authorship network for statisticians. So every point, every node is a person. The size of this node represents the number of publications that this author has, and the edge sides and the two nodes are connected if those two persons have been authoring a paper together. So the thicker the edge, the larger is the number of papers that they have been co-authored. It is also possible to group those nodes depending, for example, for the specific type of studies that they have been performing, people in statistics for education, or in economic statistics, or demography, or whatever. And this might provide some understanding of what is happening in a field, for example, trying to understand which are the people that are working together, or the communities of people actually working together. And as I was mentioning at the very first, internet is a network, and trying to understand the structure of this network that is growing and changing every day might provide an understanding of the network in itself, and also the possibility to improve its performance. But as I said, the networks are everywhere. For example, in biology, in molecular biology, we might, for example, model interactions among proteins using a network. We know that more complex organisms are organisms in which there are more complex interactions between proteins. So the proteins interact to each other to form more complex complexes, and these are able to perform more complex functions. Also, we can model protein DNA interactions using the networks, but also the metabolism, for example, can be modeled using networks. So starting, for example, from an analytic description of the metabolism, so from the stochastic equations, a set of ordinary differential equations, we can study this system of equations at the steady state, and from this we can use a network model, to study the behavior of the metabolism, and we can try to understand, for example, which are differences between somebody that is affected by some disease and somebody that is just healthy. There are co-expression networks and many others, but I don't want to go into the details. Let me just make a small joke about networks. So for example, one could look at a social network in which, as I said, individuals are connected by some form of friendship, and say, okay, this is a network. Then one might look at biology and look at protein-protein interaction networks, in which, again, as I was mentioning, proteins are connected by interactions if they interact to form some complex. And then we can look at chemistry, in which, for example, we can have some compound in which we use the carbon atoms as nodes of these networks, and the bonds, the sigma electron bonds, as connections between those atoms. So as mathematicians, what we say is, oh, they look all the same. to me. And we can call, therefore, graphs. So mathematicians try to generalize a concept, but sometimes they give some kind of strange, how do you say, name to those things. In the rest of this talk, I will call networks. For me, networks and graphs will be almost the same thing. Although, depending on the disciplines and on the specific topics, of course, there are some differences between the two. But still, for the sake of this presentation, I will use those two terms interchangeably. So, as Poincaré said, mathematics is the art of giving the same name to different things, although this name sometimes might sound a little bit strange. So let's start from the definition. As I said, the network is formally defined as a pair of sets. The set V that contains the unique nodes, and the set E that contains the unordered node pairs. So Vi Vj is a pair if there is an edge between node Vi and the node Vj. There are many different type of networks. If the edge, for example, has a direction, I can only go through it in one direction, then the network is called directed. In some cases, we have acyclic graphs, so there is no way starting from one node to come back to the same node using a path inside the network. And whereas we have a cyclicity if there is the possibility starting from one node, following a path, so jumping from one node to the other to come back to the same node. And this can be weighted, so we might have weights both on edges or on nodes. In some cases, we can have vectors of weights, so we can have a vector with many different characteristics that somehow characterize either the node or the edge or both. It depends on the application. And finally, we have loops, so we have self-connections. These are sometimes present. For example, a protein might interact with itself and enhance its performance, or it can be some synthetic connection that is added in order to make the algorithms work. Then we have multigraph. Multigraph is in general a situation in which we have multiple edges that are connecting the same nodes. Of course, this is not these are not only the networks. There are many more types of networks that exist, like bipartite networks, in which multiple type of nodes exist within the same network and so forth. But so far, we will just keep this definition. And to represent a network, the easiest thing that we can do is to use what is called the adjacency matrix. So the adjacency matrix has as many rows and as many columns as the number of vertices of nodes that are present in the network. So in this example on the right, we have 5 nodes. So the adjacency matrix that is in the bottom right has 5 rows and 5 columns. And we put a 1 in position row I, column j, if node I is connected to node j. In this case, since the network is not directed, if V1 is connected, for example, with V3, then we put a 1 here, but we also put a 1 in column 1, row 3, because we have also V3 is connected with V1. So in this case, A is a symmetric matrix. In many real applications, those matrices are very sparse. So the number of edges is very little when compared to the total number of possible existing edges. For example, this is a kind of old counting statistics related to the Facebook network, in which there are billions of people, but of course not all of them know each other, are friends of each other. So the number of edges is much, much smaller. And there are also other representations that we might use. This pretty much depends on the algorithm that we are going to use. So some algorithms might use some data structures in order to reduce their computational complexity. So one possibility is the edge list. So I just list, that is the first on the left, I just list the edges that exist in the network. This has the disadvantage that if there is a node that has no connection, it will disappear from this representation. Or we can have the adjacency list in which we say node 1 is connected to, for example, 2 and 3. Node 2 is connected to 1, 3, 5, and so forth. The adjacency list, of course, duplicates some of the information because, as we said, if the network is undirected, if 1 is connected with 2, then 2 is connected with 1. So in this adjacency list, somehow we are repeating twice the same information, but still it might be very, very useful, for example, when we look for paths to go from one node to another. And depending on, as I said, the application, one of those representations might be more suitable than other for some specific tasks. But what are those tasks? So what are the tasks that we can actually perform on in terms of machine learning and artificial intelligence tasks that we can perform on networks? Well, first of all, what we can do classification and regression. So what we can do in a network, we can try to predict, for example, the node label of a node, or we can try to predict if an edge is going to appear at some point in time in the network, or we can try to group together nodes that are somehow more similar to each other, so somehow finding communities within the network, or finding some network similarities. So how similar are two subnetworks? So let me start with the node classification. We have a certain number of nodes that are that have either a yellow, let's say, label or a green label. We have some nodes for which we don't know this label. This might be a preference in buying some product or whatever in a social network, and we want to predict what is the label of this node. So we apply some machinery, some algorithm in order to obtain the node labels for those nodes. And an example of application is, for example, protein function classifications. In human body, there are over 100,000 proteins, and we don't know the functions of all of those. So what we can try to do, starting from a network of, for example, of protein-protein interaction network, we can try to predict the function of a protein looking at the characteristic of a sub-network close to this protein. Another example is to try to predict if a link will appear. So we know that there are a certain number of links connecting nodes. What we want to do is to try to understand if a new link will appear at some point. So in some cases, this will happen. In some other cases, this won't happen. So this is again a classification problem. And an application of this, a funny, let's say, application of this is about mafia meetings. So in this work that is pointed here on the top bottom right of the slide, the authors tried to understand how mafia communities work. So we have in particular the members of two families, Mistretta and Batanesi. The double-circled nodes represent the subjects that are somehow have been investigated as being leaders, boss of those families, and the red and the yellow represent bosses in other districts. And what we want to know, and the white knots represent some other subjects that are known to have some connection with those mafia families, and what we want to understand if some of those people will connect to each other. So this is, of course, something that comes very useful in Italy in trying to get rid and to dominate this problem of mafia in some regions of Italy. So this pretty much represents, this is not very different from what happens in machine learning. So in machine learning, when we start our process, what we do, we take some raw data, we structure the data, so there is a process, a data engineering process that is used to structure the data and to obtain some characteristics, some covariates, some variables to define the observations that we have in our data set, and then on this structured data, on this table of data, we apply our learning algorithm, and the learning algorithm provides us with a model, and we can use this model to obtain predictions, as I was mentioning, on node labels, on edge predictions, and so forth. As I said, there is this step between the data collection, so the raw data, and the structured data that is usually called the feature engineering. So the discovery of some characteristics that are able to describe each observation in our data set. The downstream prediction analysis, as we said, is usually a regression, classification, or whatever, outlier detections. Of course, there are many possibilities to analyze this data. Now, what happens somehow for networks is that we do not engineer features anymore, but we automatically learn features. So what we do to automatically learn those features is to start from a network, and for example, taking a single node, we try to obtain a vector representation in some d-dimensional space. This is usually called a feature representation or an embedding. So we embed each node of the network in a vector space. Once that we have this vector representation, we can decide which are the nodes that are closer to each other, that might form a group, a community, or whatever, or we might perform some other tasks. This is something that is slightly different from what happens, for example, in the studies of images, or simple sequences, text analysis that is usually performed. Because in deep learning, many deep learning methodologies are taught to address a problem in which we have a fixed size for the images, so we can take the image, we can represent it through a grid, and then apply on this very structured model the algorithms. For example, this is the same when we think about voice recognition or also text analysis. We have a sequence that is very well structured, and we can apply our algorithm. What do those algorithms do? They just perform some operations in a very specific way and structured way. And in this case, the situation is simple. It's simple in the sense that this can be implemented on very high performance hardware in very simple way. The important thing is that we organize our data structures in terms of tensors, and the operations that we want to perform in terms of tensors. And in this case, it will go very fast on those GPUs, for example, on these graphic processing units that are the hardware, the accelerated hardware that nowadays drives the development of all artificial intelligence architectures and tools. So, but as I said, I would like to give an historical perspective of how to analyze graphs how to analyze networks and graphs. So the first approaches are based on the fact that we can try to extract some statistics or features from the network and use this as a representation of either the node or the complete graph. There are so many of those. For example, we might use the node degree, so the number of edges that are outgoing, ingoing from a specific node, or we can use some centrality index like eigenvector centrality, or we could use some clustering coefficients. All those statistics somehow are used to represent locally or globally a network. So using for each node a certain number of characteristics, we end up with a vector that describes the node. So in this case, we might try to apply, as I said, the standard machine learning and artificial intelligence technique in order to perform our analysis. Somehow, this is a little bit limited because, for example, if we have a group of networks and we try to represent each of those networks using those characteristics, then we might end up in the same representation for very different type of networks. For very different type of networks, the vector would be the same, and in this case, whatever we apply after will not be able to represent and distinguish the two networks that look exactly the same in that representation. Then there were kernel methods. There is a huge literature in this. There was a very beautiful paper that appeared in Journal of Machine Learning Research that is called Graph Kernels, and this opened the possibility to actually use standard kernel methods in two nodes. So somehow a more modern perspective, a more modern approach to the analysis, to the representation, the embedding, and the analysis of the nodes is provided by what is called node embeddings. So node embeddings, again, what they do, they use a function that we will call an encoder to obtain a representation in a vector space, in this embedding space of each node. So we take two nodes. In general, those embeddings are pairwise embeddings, and they are used, they encode those nodes in order to obtain a vector for each of them. This will use some characteristics of those nodes, so it will somehow use some characteristics of the nodes to maintain, for example, the situation in which two nodes are close. So if two nodes are close in the network, in their representation in the vector space will be close. So we have this encoding, and then we have another part in which we have a decoding of this. So in the encoding of the node, we obtain this vector, and when we decode this vector, what we try to do is try to recover the structure of the neighbor, for example, of this node. So somehow those encodings should maintain the characteristics, the structural characteristic of the networks, so that we are able to encode and then recover in the decoding phase the structure, the local structure of the network. So in general, this encoding is a function that maps the set of vertices of the network in d-dimensional space. And in general, we can call this a shallow embedding, in the sense that there are no parameters that are somehow shared among those networks. We will see that there are more advanced and up-to-date techniques that actually use this information and provide very interesting results. So in general, if we want to understand which is the representation of a certain vector we can usually use an embedding lookup. So we will end up with a matrix in which on each row we have the representation of on each node. So this matrix, the matrix that encodes the node, will have as many rows as the vertices in the network, and as many columns as the dimension of the space in which we are embedding our representation. So, and this is, as I said, a very simple representation. For example, what we can do, we can try to go beyond this very simple technique, trying to use the node features of local graph structure around a certain node to generate the embedding. So the embedding is somehow is taking advantage, as I was mentioning, of the structure of the local structure of the network. So this encoder, as I said, is the role of the decoder. So we encode obtaining the vector. The decode gives us back some graph statistics, and this should be able, as I was mentioning, to reconstruct, for example, the topology around the node. So, for example, if we have a certain embedding using ZU of a node U, the decoder might try to predict and to somehow to give us back the set of nodes that are neighbors of the node U. So the ones that are the other nodes that are directly connected with the nodes that we are on which we are focusing. In general, those decoders are pairwise decoders, and in the sense that takes two nodes and provide a real positive number. And this can be somehow interpreted as decoders can be interpreted as predictors for the relationships or similarity that exist between a pair of nodes. So let's make an example. Let's say, for example, that we want to obtain this representation of each node U using this vector V. And as we said, the decoder should tell us some information related to the fact, for example, if two nodes are similar or not similar. So the decoder of ZU, ZV will be somehow, what we are trying to do is to obtain a decoder such that the decoding of ZU and ZV is approximately equal to some similarity measure existing between the nodes U and V. So the decoder takes the vectors and gives us back a value that somehow represents a similarity measure that we have decided, that we posed. For example, the similarity matrix might be the adiacency matrix. So as we have seen before, the adiacency matrix is the matrix that says, yes, those two nodes are connected, or no, those two nodes are not connected. So in general, in order to obtain this in order to obtain those encoder-decoder structure, what we do is to minimize the empirical loss function L over a set of training nodes. So we take a set of nodes, node pairs, and we try to minimize the loss function of this decoding, where we have S as our similarity function that we have defined. So as we can understand from this, somehow the decoder will somehow measure, let's say, a distance between the vectors of the two vector representation, will give us a similarity of two vectors. The similarity measure will tell us something that is related to how similar are the nodes in the graph. And what we want to try to do is to try to minimize this loss function. So playing on those three ingredients, the decoding function, the similarity measure, and the loss function, then we can obtain many or nearly all possible embedding methods. So let me make an example. For example, for example, like Laplacian eigenmaps use as a decoder, so it measures, the method measures the distance between the vector embeddings of two nodes using the difference of the vectors in L2 norm, in squared L2 norm. The similarity measure is quite general. We can decide which one to use, and the loss function is somehow proportional to the similarity function. Then graph factorization, graph representation, HOPE, deep walk, node-to-vec, which is one of the most famous among the algorithms that are used in this field, are actually based on somehow putting together those three ingredients. There are many different, as I was mentioning, those techniques somehow come and belong to different, let's say, group of approaches, different approaches. So the first type of approaches are factorization-based approach. So in this view, in those factorization approach, we somehow look at the problem from the perspective of matrix factorization, and this is due to the fact that somehow decoding the local neighborhood structure of a node is a problem that is closely related to reconstructing the entities of the graph adiacency matrix, and this can be seen as a matrix factorization task, as what we are trying to do is to find a low-dimensional approximation of this node-node similarity matrix S, where this S, as I said, is some form of generalization of the adjacency matrix and captures some of the similarity, similarity properties of the node. So one of the first methodology in this group of technique is Laplacian eigenmaps that somehow is built on spectral clustering. And in this approach, as we have also seen from the table that I was providing before, the decoder is nothing but the L2 distance between two node embeddings, between the two vectors that we are obtaining, and the loss function is a linear combination of these of the values of this similarity function weighted by the values of this decoding function. And what we are saying here is that what we want to do is to penalize the model when two nodes that are very similar to each other have embeddings that are very far apart. So in this case, we are penalizing with higher values the single elements of the linear combination. And if S has the properties of a Laplacian matrix, then the node embedding that minimizes the loss are exactly identical to the solution of the spectral clustering. Depending on the dimension of the space in which we are embedding, we will choose a specific number of eigenvectors of the Laplacian matrix. And if we assume that is actually those eigenvectors are those eigenvectors that are related to the smallest eigenvalues of the Laplacian matrix, excluding, of course, the zero eigenvalues. So when there are another group of methods that rely on a decoder that is based on an inner product, So what are we saying is that somehow the similarity between two nodes is proportional to the dot product of their embeddings. And among the many methods that are in this class of methods, there is graph factorization, the graph rep, and the hope. Then there are the inner products methods. So in this case, what we do, we combine the decoder with the mean square error function that we see in this formula. So we try to obtain the decoder in such a way to obtain the embedding in such a way that the decoding of those embedding is as close as possible to the values of the similarity matrix in L2 norm. So and the methods are slightly different from each other, and this depends on how we define this similarity of this node-node similarity between nodes of the network. So in case in which S is exactly the adjacency matrix, we go back to the GF method. When S is something a little bit more complex, like, for example, a linear combination of the powers of the adjacency matrix, then we end up in graph rep and so forth. There is a third type of a third group of methods that somehow use something that is not strictly deterministic. So what we try to do is to have two nodes. We say that two nodes are similar if, for example, they tend to occur in the same short random walks over the graph. So what we are trying to do is to use the concept of random walks on graphs to assess the similarity of two nodes. Two nodes are similar if they appear over and over along the same shortest random walk on the network. And in this realm, we have two famous algorithms. One is deep walk, and the other is node to vec. And the main difference between those two nodes is the way in which they define again the node similarity and the decoder function. And those methods do not use directly the matrix A, but what they try to do is to optimize the embeddings using some statistics related to the random walks. So the goal of the embedding, of learning the embedding, for example, the goal is to learn an embedding, for example, for which the decoder function has this formulation in which PGTU given V is the probability of starting at node U, of visiting a node V using a random walk of a specific length, of T length. And usually T is, for example, a one-step length, a two-step length path. So in this case, two nodes are similar if the probability of from one node to reach the other in one step is very high for a random walker. A random walker, of course, is a walker that is sitting in the node and chooses one of the available edges at random. And the key difference with the factor space-based approaches is that in this case we are introducing a certain amount of stochasticity, and of course there is an asymmetry. And the two techniques are somehow using a slightly different loss function. And in general, the aim is to minimize this loss function that in this case is based on a cross entropy loss. So we are somehow using the minus log of this decoding of the two vectors ZU and ZV, and we try to minimize over the training set of nodes. And in this case, for example, there have been many different proposals, and in particular, node2vec, that is one among the most famous algorithms that is still very much in use. And it is based on the idea of word2vec. So to give on the idea that were used to represent words in a vector space, the similarity among words in some context in a vector space. So this is the proposal that was given in this paper that dates back to 2016. This has tens of thousands of citations because this technique is really very interesting. So, but what are the limits of those shallow methods? So we have two main limits. The first is from a statistical perspective, the fact that somehow we do not have any parameter exchange in trying to obtain the representation of the vector for each node. So from a statistical point of view, this might somehow provide a not very powerful mechanism. So in some cases might provide some poor results. On the other, in some cases, but those methods work in many applications. On the other side, from a computational perspective, when we go to matrix factorizations or other methods of the same type, then what we have a high computational complexity. Nowadays, we have networks that have hundreds of thousands of nodes and hundreds of thousands of edges, and of course we don't want an algorithm that is n-cube or whatever, or even n, if n is the number of vertices in the network, computational complexity. So for this reason, we now shift our attention to what are called the graph neural networks. So, and in this graph neural networks, somehow we are using the methods, the ideas that have been used in deep neural networks, and we try to adapt this to the situation of graphs. As we said, the problem with the graphs is that we have no structure in the data. We do not have many images, all of the same dimensions that we can grid and analyze in a very specific way. But rather, or we do not have a string of text on which we can move a window and we can analyze this. But rather, what we have a more complex structure, a more complex object that is the network, in which one node might be connected with hundreds of nodes, some other might be in a part of the network that is much more sparse, and therefore those techniques need to adapt to those situations. So somehow what we need to define is a new kind of deep learning architectures. First of all, what we need, the first idea that might come to mind is, okay, let's take the adjacency matrix. Let's put every row of the adjacency matrix one after the other. So what we do, we flatten the adjacency matrix in the same way in which we might do the same technique that we might use on images, and then apply some multi-layer perceptron. The thing is that somehow, if we change the order of the nodes in the adjacency matrix, then this representation, the flattening, will change, and therefore we will obtain a different result. If we have an image, the rows will have only one possibility to be stick one after the other, or the columns, or whatever we want to do, but there is an intrinsic, let's say, ordering among these. But in a graph, we might decide to change the numbering of the nodes. This will have an effect on the adjacency matrix. The adjacency matrix will be permuted, and therefore, if we apply this idea, we will get, every time that we do a permutation, we get a different result. So what we are looking for are methods that are either permutation invariant. So they are not affected by exchanges of rows and columns in the adjacency matrix, or that are permutation equivariant. So if we apply permutation to the adjacency matrix, then the result will be the same as if we apply the permutation to the f, our function that is actually that we are using. So permutation invariance means that the function f that we are using to obtain the embedding does not depend on arbitrary ordering of rows and columns. Whereas permutation equivariance, as I was mentioning, is that this permutation is consistent. So f is permuted in a consistent way as we permute the elements in the adjacency matrix. And in particular, all the methods that we have been so far, so the ones that I was describing as shallow encoders, are permutation equivariant function. And this is the main thing that we need to think. There is also another explanation for this that is a little bit deeper, and we will not go inside to this. And this is somehow based on the possibility to recognize isoformic graphs using those methodologies. But we will not go into this because this is something that is this is a little bit technical, and it's out of the scope of this presentation. So we can describe this message, this neural message passing. This is for historical reasons, we call it neural, but there are no neurons here, so it would be better to talk about differentiable function, something a little bit different, but still, let's stick to the definitions that are usually given in literature in order to describe this extension of deep neural networks to graphs, and we will focus. So we will try to represent those techniques using the standard way of that are used in artificial neural networks, and therefore we will talk about this message passing technique. What does it mean? So somehow what happens when we use a graph neural network machinery, we produce an hidden embedding. So at each iteration, let's say, we build the network, and little by little we update this this vector that represents the node using some information that comes from nearby nodes. This operation is usually called an aggregate operation. So what we do is we aggregate the nodes that are, for example, near, for example, in the neighborhood of a node. We take the information of them, we aggregate in this, and using this aggregation, we update the representation of the vector for the node. So at the first step, for example, I might look at my neighbors. So I might look, I am a node, and I look at the nodes that are directly connected to me. In some way, I take some information from those, and I aggregate this information. For example, I might have some node characteristic, and I might take node characteristic and compute the average of those characteristics of the nodes that are around me. Then I use this information to obtain this first representation of my vector, my embedding, hidden embedding vector. At the next step, my neighbors will take information that come from their neighbors and will pass this information to me. And I will update the representation of the embedding using this representation. So there are two steps. One is the aggregation of the information that comes from, let me see if I can use a pen. So one step that is the aggregation of the information that comes from the nodes that are in a neighborhood. So for example, my first neighbors, the nodes that are directly connected to me, and I use this information to update the hidden representation of the vector. So one step at a time. What I do is I update this embedding vector. What happens here is that somehow this has some limits. So what happens is that if I explore the network, because somehow what I'm doing is, at the first step, I look at my neighbors. The node looks at its neighbors and gets a representation. At second step, it looks at the neighbors of its neighbors. So starting from the node, we are exploring locally our graph. This is usually, it is not usually very useful to go too far. What happens is that if we go too far, the vector representation that we obtain for the nodes are almost all the same. So we have a phenomena that is called oversmoothing, in which advancing in the exploration of the network has the drawback of somehow providing the same representation for all the nodes. And of course, this is something that we don't know, because we cannot distinguish anymore between the nodes of the network. But again, so if we look at these graph neural networks, these graph neural networks can be explained by those two steps: update and aggregate. Now, depending on how we decide to aggregate and how we decide to update, we will get the many different architectures that are available. So, as I was mentioning, at each iteration K, we aggregate the information that comes from the neighbors of node U, and so that are in a neighborhood of node U, and we generate this message, we call it M, that somehow is used to update the embedding that we obtained at step k-1 to obtain the embedding at step k. So the initial embedding will be the set of node features that we have. Then at step after k iterations, so after k message passing step, we will have the output of the internal layer will define this representation, this vector aggregation. And these aggregate functions is defined in such a way that what we obtain is permutation invariant by design. Now, unlikely to what happens to shallow embedding methods, you remember we were talking about adjacency metrics. So we had no possibility to use information that are related to the node. So we are not considering in shallow embedding, we are not taking advantage of some characteristics of the nodes. On the other hand, GNN require node features. So we cannot have this message to update and blah, blah, if we do not have some features that describe the node. So this is on one side something that is can be seen as something that provides more possibility to describe the network. On the other side, if we have a network in which we do not have node features, still we can use GNNs, graph neural networks, but we have to somehow invent those node features. So there are many ways to do this. We can use some one-hot encoding feature, which, for example, represents the identifier of the nodes, the node labels, or there are some other tricks to give some characteristics to the single node. So this we have already discussed, how from each iteration we go over and over exploring the neighborhood of the node. And this information that those embedding graph neural networks, those embedding encode are structural information about the graph, because we are looking at the neighborhood, plus these field node characteristics. And as I was mentioning, the problem of this mainly relies in the fact that we might end up in a representation of the nodes that is all the same for all the nodes if we explore too far from the node, if we explore the graph too far from the node. So somehow, as I was mentioning, now we have the opportunity to embed, to use these features that are related to the nodes. And somehow this is very similar to what happens, for example, in convolutional neural networks, in which we look at patches, for example, some spatial patches of the image or whatever we want to analyze, and we aggregate on those patches and the information in a very similar way to what we are now doing in the graph, using graph neighborhoods. So somehow, in some cases, it is interesting to give a formalism for graph neural networks and to formalize this update and aggregate function using somehow some matrix vector operations. So the message passing can be defined as a matrix vector multiplication. This is again the message. This is the hidden embedding at step k, in which we have two matrices that we need to learn. So we have those two matrices. This is a bias term that is sometimes is hidden to make the notation simpler. And here we have a function that is a nonlinear function. So, for example, it can be an hyperbolic tangent, a ReLU function, or whatever. So again, let me again look at the picture. And now what we were, so now our representation is obtain the message and update the representation. And this can be expressed in matrix vector form. This can be useful in some cases. In other cases, this can be too heavy, especially when the graphs are very huge, very large. As I said, the fact that we express those algorithms, this message passing using tensors is very useful if you have a very structured problem. It becomes less useful in case of graphs in which the matrices that we are handling, the graphs that we are handling are very sparse. And so in this case, we have a very huge objects, tensors to use. And so it's not really useful. But nevertheless, to have a direct connection with the theory that has been developed in the case of deep neural networks, it is somehow useful to represent these message passing mechanisms using actually the graph adjacency matrix. As I was mentioning, the problem here is that one node might have many neighbors, another node very few. And our message takes information, aggregating the information of nearby nodes. But those nodes might have a different information content, in the sense that some of them might provide some more important information, some others might provide less important information. So I should be able to decide which are the nodes around me that are more important to obtain a representation of the node in this vector space that is somehow useful for my analysis. So, and here comes into play the notion of the attention. So this attention, you might remember this paper that was called "Attention is All You Need," that somehow gave rise to all the class of transformers. So modern large language models are based on transformers, and those architectures are based on the attention mechanism. So here, when we aggregate the information that come from nearby nodes that are in the neighborhood of the node, then what we do, we weight those nodes. So we weight this contribution, and this is called attention. So the fact that we put our attention, we weight more some of the hidden embeddings of some of the nodes that are around with respect to others is called attention. And depending on the type of attention mechanism that we use, we end up with many different algorithms. And also for graph neural networks, we can take advantage of the fact that we might use different mechanisms together. So we might use what is called multiple heads. As we know, all the transformers, all recent transformers have a multiple head attention mechanism that provides incredible results in some application, and this can be extended and can be used also in this realm. In this case, we do not have a matrix of weights, but rather we have a tensor of weights that are used in order to obtain the message passing step. So somehow these are very generally speaking, the literature in this field is huge. So it's also difficult to keep track of all the papers that come out. And somehow the big lack that there is that there is no theory among those. So we can try to have a taxonomization of the methods, but in the end we don't know when those methods work, in which applications, and for which data. So there is a no-free lunch theorem. There is no single technique that can optimally solve all the problems that can provide optimal embeddings in all the things. But rather, and I think that this is a very important field of research, we should try to understand what is the information that is really contained in the data, and what is the impact on the algorithms that we apply. So I think that still starting from the data, we might find a way to model the information content, and therefore which might be predict the characteristics of those so the performance of those graph neural network methods. So far we have been talking about single graphs. So we're taking the nodes, for each node, we were trying to obtain a vector, and starting from this vector representation, we were trying to do node classification, edge prediction, and so forth. But there are many applications in which we do not have a single network, but rather we have a family of networks. So we have a set of graphs of networks, and what we want to do is to obtain an encoder that assigns to each of those graphs a vector. So a function that starts and taken a single graph, complete graph, complete sense, a single graph in a family of graph provides a vector representation in some d-dimensional space. So in this case, there is only one vector that is associated to the whole graph. And once that we have such a technique, and this encoding should preserve some proximity measure, as in the case that we were mentioning before, in this case, we can do many different things. This is an example. For example, this is an example. Suppose that we have 200 networks divided in two classes, the blue class and the green class. What we want to do is we want to take all them together and embed this vector space in order to have a vector representation, and maybe applying some clustering technique or some classification technique, or just to visualize those graphs. Are those applications important? Yes, of course they are. For example, here there is one of the first that appeared, in which people were trying to model brain diseases using a network. So what they were doing, and this is something that still people do, and actually it's something that is in production, let's say, in many different diseases, like, for example, Alzheimer, or others, in which what they do, they use MRI, magnetic resonance instrument. So what they do, they take the signal that are produced by our brain, and those signals are mapped to different parts of the brain. So there are atlases. Very recently I heard that there was a new atlas on brain that has, I don't know how many parts it is composed. So an atlas somehow divides the brain in functional areas. To each area is associated a function or a process, and what we try to do is to give a stimulus to the brain of an Alzheimer patient, of a control patient, and we try to understand how the parts of the brain react, and we try to see if there is some correlation among those signals. So what we end up in a correlation somehow network that represents the fact that signal coming from different parts of the brain are correlated, and then we compare the network of a disease patient with the one of an healthy patient to understand which are the differences. So what is changing in the brains of those two. To do so, for example, we will need to analyze, I don't know, a few hundred patients that have a disease with respect to a cohort of control people that has no disease, and then we try to understand the statistical differences between or among those networks. Again, the approaches for full graph embedding lie in the main fields that we have already seen: matrix factorization, graph kernels, and neural networks. I will not go into the details of this because I think I have 10 minutes or so. I don't want to take all your time. I want just to show you one that is interesting and that, in my opinion, might be generalized. So maybe you remember that we were talking about node to vec. That was this technique that was somehow using random walkers, the idea of random walkers, in order to obtain a representation of a single network. The extension of these two graphs, so representing one vector for each graph, is called the graph to vec. This graph to vec is based on a technique that is called doc to vec. Doc to vec is a deep neural network that takes a set of documents and represents each document using a vector, in which two documents that are similar for their content, for the meaning of their content, will have a very close vector representation, whereas documents that talk about different things will have a very different representation. This is very useful, for example, when we try to model I don't know, for example, for movies. We have the description of the movies. We want to understand which are the movies that are more similar to one another, so that when the customer comes and asks for a movie, we can recommend another movie that is very similar to that. So this is This is what doc2vec does, and graph2vec does something very similar in the sense that it takes for each graph, it uses graph2vec that is based on skipgram to obtain a vector representation of the graph using, rather than a sliding window moving on the text, that is what is doing actually the document2vec, it actually looks at subgraphs that are rooted in one specific node. So now the words are those the nodes that are describing the graph are obtained looking at subgraphs of increasing dimensions that are around each node. So each node of the graph obtains one or more words. The set of words will represent the text that describes the graph. We take those words and we give to doc2vec. And doc2vec will say, oh, look, the vector representation of those two graphs is more similar than those two, and so forth. So this is a very interesting idea, a little bit esoteric in the sense that we start from graphs, nodes, and the characteristic of a graph to end up in a string representation of the graph. So there are strings that represent the nodes of the graph that we use to feed this doc2vec, but still it works pretty well. So we decided to slightly change those ideas of graph2vec, and what we did was to introduce this netpro2vec. We published it, actually the online version was 2021 to 2022. So 4 years ago, 3-4 years ago, we ended up with this methodology. And our idea was actually to change the way in which we explore the graph. So we don't want, you remember the message passing mechanism in which I go to the nodes that are near to me and somehow I average the vector representation of my neighbors. We decided that this was too simple, that somehow, as I said, you cannot explore the network in depth because otherwise you go towards over smoothing. And therefore, this was not sufficiently powerful. So we decided to have a different representation. So let me see if I can explain what I mean. So suppose that we have this network. Okay, we have only 6 nodes, and we have some weights on the edges. Okay, so suppose that I am sitting in node 1. Okay, and I ask myself, which is the probability of starting in node 1, for example, for a random worker, choosing one of those edges at random to jump to node 2. And well, what I need to do is to take the weight that is in this case 2 and to divide by 2 plus 5 plus 1 by 2. And this gives us this number 0.2. Okay? Then I can repeat this and I can say, which is the probability of in one jump starting from node 1 to arrive in node 3? And I compute this probability, and so forth. And I can compile this, repeating this for every node in the graph. I can compile this table that is called the transition matrix. Another thing that I can do, and so what I obtain is an empirical distribution on every row that describes, of course I need to sum at 1, that describes the neighborhood of a node. So what I do is I order those numbers. So if here I have 0.5 and then I have 0.2 and 0.1, what I do, I take this word that says this word was obtained using TM1, and the nodes are ordered starting from node 2, node 1, node 6, and node 7. So I just order them. I can decide to threshold this. So, for example, I can decide only to take the nodes for which this probability is higher than a certain amount or whatever, but still I end up with a string that is composed by the labels or the red labels of those nodes that I obtained in this way. I can do the same, for example, using what we call the node distance distribution. So I sit in a node and I ask which are the fraction of nodes that are at distance 1, so that are directly connected with me, and which is the fraction at distance 2, 3, and 4. And of course, this can be extended, as in this case, to weighted graphs. And again, what I get is an empirical distribution. Okay? Of course, I can go as far as the diameter of the graph. I cannot go any further than that. Again, I set up this word, and all those words that I obtain, one for every representation, we say empirical probability distribution representation, one for every node, the set of words represents the corpus that describes the graph. I feed the doc to vec. I have some documents, some strings that represent each graph. I feed the doc to vec, and this actually gives very interesting results. This is, as always, in this, there is some alchemy in those graph, in those deep neural network. We used the Lanziganetti Fortunato Radicchi software for generating two groups of networks that had a different structure. So this software is used to generate random graphs and to study community detection algorithms. But we decided to take some graphs for which the number of there were more communities, and some other graphs in which there were less communities, and see if this mechanism might actually discriminate those two type of networks. So we have 600 networks that are of this type, so that have a certain number of communities, and we have 1,000 networks that have no communities. Is this machinery able to discriminate between the two? The answer is yes. And this is the t-SNE representation of the embedding of those graphs. So this is the classification is done in the d-dimensional space. This is only the representation in a b-dimensional space, just to give some evidence. And as we can see, in some cases, this net-pro to vec using some specific type of representation of this probability, empirical probability distributions might provide very interesting accuracy results, and also, as it is shown in this bidimensional space, also a very interesting discrimination among the two. So the last 2 minutes that I have, I would like to point at some research direction. So there are many, they are all interesting, and I think might attract some young or in Italy we say differently young researcher to those topics. So the first is the expressivity. So there is a lot of studies that say, oh, look, this graph neural network is not able to distinguish those two small graphs that are completely different, in the sense that it provides the same vector representation for two graphs that are not isomorphic. So there is all a discussion about isomorphisms. Now, this is, of course, a very interesting problem, but I think that in application, we are more interested in understanding if two networks are similar or not. We want to understand if two Alzheimer's patients share some characteristics. We don't want to understand, we don't want to know if they are exactly the same or not. This is somehow a limited view of the problem. So all the studies that are related to expressivity, I think that they should somehow be viewed in this light. So not only the capability of actually discriminate or give the same representation to isomorphic graphs, but also to measure, so to obtain graph neural networks that are really able to express the similarity or dissimilarity existing among the networks, and this in the light of the computational complexity that is involved in those machineries. Those machineries require huge amount of computations. Then another topic that in my idea is also very interesting is the generalization. So many of the techniques that we are using are transductive. What does it mean? It means that if we have a group of 200 patients, 400 patients, we can build the embedding. But if a new patient arrives, we don't know how to embed in this vector space. Because, as we said, it all depends from the others. So in this message passing mechanism, we update the information using the neighbors. So somehow, if I add 1 point, the embedding will, if I add 1 graph, the embedding will completely change. So we should start to think more in the light of inductive methods, so methods that are able to provide a representation, an embedding that is general enough so that when I try to embed a new graph, the embedding doesn't change. And this is, of course, a very interesting problem, especially in the light of the fact that to train those machinery, we use very often a huge amount of data. So, and sometimes we cheat using synthetic transformed starting from the real data, we change the data a bit and we throw in the training set and so forth. So we should try to understand how those embedding techniques generalize, are inductive with respect to data augmentation, and also how we can make those machinery generalize to out of the sample distribution. So this means two things that are two observations that are drawn from different distributions. So the last 2 points are also very interesting. I will stop here because my time, I think it's over. I don't want to be long. And let me see if I have this picture here. Okay, so and these are 2 beautiful books that I would suggest everybody to read because they are very simple and are very interesting. One is from Hamilton and is also freely available. You can find open source, open content versions of the book that you can download. And also this one from Scardapana is in Rome. That is very interesting. Is a very interesting way to talk about the neural network. He never talks about neural network. He always talks about differentiable function. So this is more or less what I wanted to discuss about this topic, and I thank you for your attention.
Thank you very much, Mario. This is really very interesting. Please, questions, comments, remarks. Mario,
yes.
May I ask you, you see, in this very field, which I don't know very well, but still, you see, I have some interest. It looks like you see the general ideas of aggregation, for instance, are more or less goes to linear convolution or sometimes to nonlinear convolution, but in a very, let's say, narrow form. Why the other models are not used? You see, there are a huge number of models, and that might be really very interesting.
Yeah, I completely agree with you. You know, sometimes what we try is what it works in some these are mainly developed by engineers, practitioners. So they have a problem and they try to find a solution for that problem without any effort to generalize, to understand the theory that is beyond or anything. So what they do, they try the fastest thing. It's a more I don't know how to say a craft work in which I know how to combine the different pieces and obtain something that works. I think that this is the main reason. There is no reason not to use other forms of aggregation.
It's very interesting because then we should discuss it when you come. Maybe, or maybe I come when I come to Italy. Maybe, you see, I might give some rather wide talk on this many methods of aggregation, which might be very useful. And it's necessary to, for instance, when you talk about these brain problems, you see, that might be really, you see, it's possible to propose some other, some methods which might work. I don't know. Well, okay, we should talk about it.
Absolutely. I think there is a large, there is many possibilities to enhance those methods. This can be done either from a theoretical point of view, so starting again from scratch and trying to understand what is feasible and not, what are the results that we get. So provide a theory for all this, for all those techniques, or going to more practical, from a more practical side of the story. If there is an interesting problem, trying to understand how we can model this in the best way, let's say, in the most useful way. So I think that at every level there is the possibility to give a contribution. As I said, the field is very, as thousands of papers is something really incredible to handle. No, there are papers every week, not 100, but tens of papers. So even following the result is difficult. Not all people, not everybody use the same notation, the same way to describe methods. So sometimes they rediscover many times the same technique and they don't realize. And so it's difficult to navigate. This is the first thing, but still, as I said, it's I think it's very interesting. I was recently trying to, I was focusing on those attention mechanisms, and I was trying to use this probability, this empirical probability distribution to obtain some attention mechanisms that because somehow this is because the graph transformers in this moment work, but they don't work very well. So the direct extension of transformers, that is the thing that is behind the large language model, generative models and so forth, does not work well. And I think that this is mainly due to the fact that the attention mechanism is not suitable.
I see. Thank you very much. Okay, some other questions, please. Comments or no? Thank you very much, Maria, and I'm waiting when you come and we will discuss things.
I will let you know when I will be in Moscow.
Yeah, please. Okay.
Thank you.
Thank you very much. And at 6 o'clock we have a last presentation today. It is a presentation by Eric Moskin. Let's begin. It is my great pleasure to introduce our next speaker, my friend Eric Moskin. Professor Moskin is a professor of Harvard University, and he's one of the most famous scientists in the world, Nobel Prize winner, and I can proudly say that he is also working in our university, in our center. And so I will not go too much about your achievements, Eric, for this year.
Well, thanks very much, Fuad. It's good to be able to talk to you today. And I thought, since it's election season in the United States, the election is next week, it might be interesting to talk about some interesting work that I have done on the theory of elections, in particular, elections that are resistant to strategic voting. And the hero of this story will be Condorcet. You may know about the great 18th century French thinker, the Marquis de Condorcet, who in particular contributed many ideas behind the French Revolution, but for us voting theorists, it was his voting ideas that were most important, in particular the Condorcet voting, which I'll have much to say about today. So strategic voting. Strategic voting consists of voting insincerely in order to try to achieve a better outcome. Suppose that you prefer candidate X to candidate Y, you may nevertheless rank Y above X when you vote, because you don't think X has a good chance of winning, Y does have a chance of winning, and therefore by emphasizing Y over X, perhaps you get Y elected. Now, I think there are two reasons why voting systems which are vulnerable to this kind of strategic voting are to be avoided. The first is that if people are voting strategically, then even if the voting system looks good from a theoretical point of view, according to their true preferences, if their votes are distorted, the voting system may end up not being so good from the theoretical standpoint. In other words, if you distort the inputs, which are the votes, then you're going to distort the outputs, the outcome of the election, and there may be no guarantee that those outcomes fulfill the nice properties that you want a good voting system to satisfy. But I think an even more important reason to try to avoid strategic voting is that it's hard for voters to do it well. If I'm participating in an election, I already have a lot of work trying to figure out my own preferences. I have to study the candidates. I have to read about their backgrounds. I have to learn about their positions on the issues. And that's already quite a lot of work. If on top of that, I have to make predictions about how other people are going to vote in order to react against that in a strategic way, my decision problem is several orders of magnitude more complicated. And so simply to make life easier for voters, it's good to have voting systems which are not vulnerable to strategic voting so that voters can concentrate just on their own preferences and not worry about how other people are going to vote. So I hope those motivations are clear. Unfortunately, there's a famous result in voting theory called the Gibbard-Satterthwaite theorem, which says that in some sense, there is no voting system which is always invulnerable to strategic voting. The term is strategy proofness. Strategy proofness means that it's always to your advantage to vote truthfully, not strategically. That's quite a negative result because strategy proofness cannot be obtained. But the Gibbard-Satterthwaite theorem depends very much on what's called the unrestricted domain condition, which means that voters' preferences can be anything. You can't say in advance what you can't put any limitation on them in advance. However, we've known for many years, since the 1960s, that for some natural restrictions on preferences, we might be able to obtain strategy proofness. And in particular, if preferences are single-peaked, then perhaps majority rule, Condorcet voting, is strategy proof. Let me remind you what I mean by single-peaked preferences. Suppose that we arrange the candidates according to some ordering. I think the most convenient ordering to think of is an ideological ordering. So we have X1, the candidate on the left, and then X2 is a candidate slightly more to the right, all the way up to candidate XM, which is the candidate furthest to the right in political terms. If you have single-peaked preferences, that means that if you prefer candidate I to candidate J, who is to the right of candidate J, then you're going to so Xi is to the right of J, or Xj is to the left of Xi. If Xj is to the left of Xi, then you're going to prefer Xj to a candidate who is still further to the left. That is, as candidates move away from you in ideological space, you like them less and less. You prefer candidates who are closest in ideological space. That's a condition. It's a strong condition, but as I will show you later, it's a condition which in reality is actually often satisfied. We have evidence now from the US that people actually have preferences that look like this. So these are called single peak preferences because if we graph your utility as a function of the candidates, the graph will have an inverted U shape. It will be an inverted U shape. The peak will occur at your favorite candidate, and then the utility will decline as we move away from your favorite candidate, Xi. Now, let me remind you what majority rule or Condorcet voting is. Given voters' preferences, we want to elect a candidate who will beat every other candidate by a majority in a head-to-head contest. So X is the winner if for any other candidate Y, more people prefer X to Y than prefer Y to X. In those circumstances, X is called the Condorcet winner. And if we don't put any restrictions on preferences, there may not actually be a Condorcet winner. This is something that Condorcet showed himself. It's now called the Condorcet paradox. And here's an example of the Condorcet paradox. There are three groups of voters. 33% have the ranking XYZ, 34% YZX, 33 ZXY, and a majority prefer X to Y, these people, and these people prefer X to Y. A majority prefer Z to X, these people, and these people, but a majority prefer Y. Sorry, this should be Y to Z. Y beats Z here. These people and these people prefer Y to Z. So there's no Condorcet winner in this example. Each candidate can be beaten by some other candidate. Nevertheless, and this was a discovery made by Black back in the 1940s, if preferences are single-peaked, a Condorcet winner does exist. And let's see why that is. Let's think of each voter's favorite candidates. That's the voter's peak, if we're looking at the graph of his utility. So let xi star be the median candidates in the sense that 50% of voters have their peak, their favorite candidates, to the right of xi star, and for those voters, they will prefer xi star to any candidate to the left of xi star, because remember, by single peakness, voters always prefer candidates who are closer to them in ideological space. Xi star, for someone who has a peak to the right of xi star will be closer to the candidates, to the voters' favorite candidates than any candidate to the left of xi star. And therefore, since there are 50% of voters who have their peak to the right, 50%, a majority of voters, will prefer xi star to any candidate to the left. But this argument applies equally well to candidates to the right of xi star. A majority prefer xi star to any candidate to the right. And that means that xi star, the median candidate, median in terms of where the voters' peaks are located, the median candidates beats every other candidates by a majority. In other words, xi star is a Condorcet winner. So that's very nice. And we can actually go further than this. And this was the work of Dominant and Farquharson in the 1960s. We can investigate whether any voter or coalition of voters would ever gain from voting strategically. And we'll see that the answer is no. Suppose when voters are voting, they just submit their peaks. So what we do, here's how the voting system works. Each voter votes for her peak, her favorite candidates, and then given the peaks that have been submitted, the winner is the median candidate, the peak right in the middle. Now, what I'm saying is important, and we'll see why it's important in a little while. In other words, we're conducting the election in this very special way in which voters are just voting for peaks. Now, suppose that there was a coalition of voters to the left of xi star who were thinking about voting strategically and trying to improve the outcome. If everybody bids truthfully, if everyone bids sincerely, then xi star wins. because XI star is the median candidate. Suppose that this coalition to the left of XI star tries to improve the outcome for the coalition. Well, if they are all reporting peaks to the left of XI star, then XI star stays the median. And so an attempt to vote strategically, if this coalition attempts to vote strategically, they're going to have no effect on the outcome when they're reporting peaks to the left of XI star. And by the way, their true peaks are to the left of XI star by assumption. Now, suppose that some members of the coalition report peaks to the right of XI star. That will have an effect on the outcome because now the median will move farther to the right. If you put more weight to the right of the median, you're going to move the median to further to the right. But actually, that's exactly the wrong direction for this coalition. They're to the left of XI star. They don't want the median to move farther to the right. So that distortion isn't going to work. That distortion isn't going to work either. And so that proves that this coalition, a coalition of people with peaks to the left of the median, cannot gain by misrepresenting their preferences. They cannot gain from strategic voting. By the way, I should have said that if there are questions along the way, you should feel free to ask, particularly if there's something that you're not following. So please do let me know if you're puzzled about something. Now, obviously, this is true symmetrically for voters whose peaks to the right. Suppose we had a coalition of voters made up of people to the left and to the right of the median. Well, that coalition, it's impossible that they can all gain from strategic distortion because the voters on the left want the median to move to the left, and the voters on the right want the median to move to the right. They can't both get what they want, and so a coalition like that, made up of both left and right, can't succeed either. So we have established, and this is the Dummett and Farquharson argument, that if voters vote in this particular way, you get the Condorcet winner, and furthermore, no one has the incentive to vote strategically. Voting truthfully is a coalitionally dominant strategy. So this is a nice result in a number of respects. It could be used, for example, in voting over public goods. Let's imagine that we have a society of N citizens, and they're voting over the public good level X. We'll simplify the economy. There are two goods. There's a public good X, and there's a private good, and the public good is paid for using the private good. Let's say that the cost of public good level X in terms of private good is some function C of X. So C of X is the amount of private good needed, and as X increases, the cost increases, and there are and the cost is convex, so that the costs are actually increasing. And let's imagine that each citizen pays his share of the cost, that is C of X over N, since there are N citizens. Now, let's suppose that the citizen's utility function depends on the public good level, X, and the amount of private good that he has to pay for this public good level, which will be C of X over N. I put a minus sign in front of that because he's giving up this private good in order to pay for the public good. Let's suppose that this utility function satisfies the usual assumptions about utility functions, increasing in the two goods and quasi-concavity. Then, when a voter, suppose the voter could choose the public good level, then the voter would be maximizing this expression here. The solution to this maximization problem we'll call XA. So that would be the citizen's favorite, citizen A's favorite public good level would be X sub A. And it's not hard to see that each citizen will have single peak preferences over different public good levels. The peak will occur at XA, the citizen's favorite public good level, and it will decline in both directions as we move away from his favorite. That just follows from the utility function U satisfying the usual properties of a utility function, increasing and quasi-concave. So if citizens voted over the public good level and the winner was the median level, we would elect the Condorcet winner. Voters have an incentive to vote truthfully, and if voters' peaks are distributed symmetrically, you can actually show that this will result in the public good level that, say, maximizes consumer surplus. This was actually proposed by the economist Howard Bowen in the 1940s. So this public good application is a nice use of the fact that with single peak preferences, voters have the incentive to reveal their favorite public good level, their peak public good level, truthfully. But as we'll see, there's a problem applying this idea to political elections. Now, as I'll be coming to, there actually is evidence that in political elections, preferences are single peaked, or at least close to single peakness. I'll talk about the sense in which they're not exactly single peaked later on. So forgive me for using an American example, but I think this makes the point. Let's think back to 2016. 2016 was a contest between in the U.S. For president between Donald Trump and Hillary Clinton in the general election. And you may remember that that Trump won quite narrowly, but Hillary Clinton just barely got the Democratic nomination. She was in close competition with Bernie Sanders for the nomination. Bernie Sanders, who is still around in politics, is a quite left-wing political figure. He came fairly close to getting the Democratic nomination. Now, at that time, the mayor of New York, Michael Bloomberg, who is a rather moderate figure in politics, said, well, I'm afraid that if Sanders gets the nomination, it'll be a contest between two extremists, Bernie Sanders to the extreme left, Donald Trump to the extreme right. So perhaps I should run as a compromise candidate, a candidate in the middle. And this is just a hypothetical scenario because in the end, Sanders did not get the nomination and Bloomberg did not run. But let's follow the hypothetical through. Now, Sanders voters, people who liked Bernie Sanders would presumably prefer Sanders to Bloomberg, of course, but they also prefer Bloomberg to Trump because Bloomberg was closer to the Sanders voters ideologically than Trump was. Trump was on the far right. And similarly, Trump voters presumably preferred Bloomberg to Sanders. So if we tried to mimic what we did for the public good election, we could have each voter vote for her favorite candidates, and then elect the median of the favorites, where Sanders is the left-wing candidate, Trump is the right-wing candidate, Bloomberg is the centrist. The problem is that doing this in practice is completely impossible because by calling Bloomberg the centrist, we are prejudging the election. I mean, we may know that in some sense Bloomberg is the centrist, but we can't. We would be giving Bloomberg an enormous advantage by officially designating him as the centrist and then electing the candidates, the median candidate according to the vote. So in the language of voting theory, trying to use the public good method for conducting an election like this would be highly non-neutral because we're giving an enormously unfair advantage to Bloomberg. So that suggests that if we want to elect the Condorcet winner in this election, we can't just have voters report their peaks and then compute the median, because computing the median would require us to decide who is the centrist candidate, who is the left-wing candidate, and so on. What we can do instead is to have voters report their rankings of candidates and then compute the Condorcet winner on the basis of the rankings. So here's a hypothetical scenario. Again, this election never took place, and so we're just guessing what might have happened if it had taken place. Suppose that the voters broke down into 4 groups, and I've indicated the size of each group at the top. They're the Sanders voters here, they're the Trump voters here, the Bloomberg voters in the middle. Now, if voters report their rankings truthfully, who will the winner be? It will be Bloomberg, because 71% of voters rank Bloomberg above Trump. These voters do, these voters do, these voters do. That's 71%. And 54% rank Bloomberg above Sanders. These voters do, these voters do, and these voters do. That's 54%. So Bloomberg gets a majority over both Trump and Sanders. And so Bloomberg would be elected if we used Condorcet voting for this scenario. But this system is vulnerable, or may be vulnerable, to strategic voting. Suppose that the Sanders voters misrepresent their preferences, and they, instead of voting Sanders, Bloomberg, Trump, their true preferences, they vote Sanders, Trump, Bloomberg. What will happen? Well, now there is no Condorcet winner. 66% of voters prefer Sanders to Trump here, and, well, actually here and here. 54% prefer Bloomberg to Sanders here, here, and here. And 75% prefer Trump to Bloomberg. Because, notice that because of the Sanders voters' misrepresentation, Trump comes out ahead of Bloomberg here, and also here, also here. So 46% plus 29% is 75. So there's no Condorcet winner. And so we have to use some tie-breaking rule to decide who's going to win. Now, you may know, if you know some voting theory, that there's a large literature on how to break the tie when there's no Condorcet winner, how to determine who should win if there is no Condorcet winner. One famous method for breaking the tie, and this was proposed by Black, the same Black who showed the importance of single peak preferences. One proposal is to use the board account to break the tie. Let me remind you what the board account is. In the board account, each voter ranks the candidates, and if there are 3 candidates, as in this example, a candidate will get 2 points every time he's ranked first, 1 point every time he's ranked second, and no points every time he's ranked third. And then the winner is just the candidate with the most points. Now, if we do the calculation, the Borda calculations for this profile up here, we see that Sanders wins. Sanders gets 112 points. Where does that come from? Well, Sanders is ranked first here, so that's 46 times 2, and Sanders is ranked second here, so that's 20 times 1, and that adds up to 112. And we can do the calculations for Trump and Bloomberg. But the point is that Sanders wins, and that means that this strategic voting on the part of the Sanders supporters actually is successful. They really prefer Bloomberg to Trump, but they pretend that they prefer Trump to Bloomberg to make sure that Bloomberg is not the Condorcet winner. And when we use the board account to break the tie, then Sanders wins. So we can show, using exactly this kind of calculation, that all of the other standard tiebreakers that are used in the literature on Condorcet voting can be strategically manipulated in this way. And so that raises the question, is there a way in a setting like this to elect the Condorcet winner in a way that is not vulnerable to strategic voting? In other words, that is strategy resistant. And I'd like to show you that the answer to that question is yes. There is a way. It's not a way that was previously proposed in the Condorcet literature. So, so this is one contribution, which I think is new to this paper. And it relies on the idea that if we look at voters' preferences in this example, and remember, preferences are single-peaked. So if you like Sanders first, you're going to prefer Bloomberg to Trump. And if you like Trump best, you're going to prefer Bloomberg to Sanders. But for the Bloomberg voters who are in the middle, they might have either the ranking Bloomberg, Sanders, Trump, or Bloomberg, Trump, Sanders. In other words, there's more diversity in preference among Bloomberg supporters than there is among Sanders or Trump supporters. The fact that there's more diversity is an endogenous feature that we can exploit, that we can take advantage of. So how are we going to do that? Well, let's begin by looking at a somewhat different voting system. It's called ranked choice voting. Ranked choice voting is similar to Condorcet voting and Borda voting in the sense that voters rank the candidates. They rank the candidates, but now the winner is the candidate who has a majority of first place votes, if there is such a candidate. If there's no such candidates, what we do is to drop the candidate who is ranked first the least often, and then check again to see whether there's some candidate with a majority of first place votes. And if so, that candidate is elected. But if not, we keep on dropping candidates according to who has the fewest first place votes until someone has a majority of first place votes. Now, ranked choice voting actually is now used in a number of places in American elections. In particular, it's used in 2 American states, the state of Maine and the state of Alaska. And I'm going to come back to that point.
Eric, is it a single transferable vote?
Yes. For those of you who are familiar with single transferable vote, this is single transferable vote in a case where there's just a single winner. Single transferable vote can be used for elections where you're electing multiple candidates to office. you're filling a council, for example. But in the case where there's only one winner, ranked choice voting is identical to single transferable vote. That's right. So we'll start with single transferable votes. And in this example, who is the winner? Well, notice that there's no candidates who has a majority of the first place vote. Sanders has 46%, Bloomberg has 25%, Trump has 29%. No candidate has a majority. So we eliminate the candidates who has the fewest first place votes, and that's Bloomberg, because 25 is less than 29 and it's less than 46. So we eliminate Bloomberg, and now these candidates have Sanders as their first place choice, and these voters have Trump as their first place vote. But now Sanders wins because 46% plus 20% is a majority. So Sanders wins under a single transferable vote or ranked choice vote election. But ranked choice voting, single transferable voting, is very easily manipulated by strategic voting. For example, suppose that in this example, the Trump voters put Bloomberg first rather than Trump. If they put Bloomberg first, say they have the ranking Bloomberg, Trump, Sanders, now Bloomberg will have a majority of the first place vote, 29 plus 5% plus 20%. So Bloomberg will be elected. And that's better for the Trump voters than electing Sanders, because remember, Trump voters prefer Bloomberg to Sanders. So ranked choice voting, single transferable voting, is certainly manipulable, but we're going to change it. We're going to change the voting system to take account of the diversity of a candidate's support. We're going to calculate each candidate's diversity score. How do we do that? Well, let's give 1 point to a candidate for according to how many. We'll give 1 point to a candidate for each different ranking of the other candidates. So Bloomberg gets a diversity score of 2 because there are 2 different ways that Bloomberg supporters rank the other candidates. There's Bloomberg, Sanders, Trump, and there's Bloomberg, Trump, Sanders. So Bloomberg gets a diversity score of 2. Diversity score can be thought of as a measure of the broadness of support for the candidate in question. So Bloomberg has a diversity score of 2. Trump and Sanders, there's only one way that Sanders is ranked first, and there's only one way that Trump is ranked first. And so here's how our election rules are going to work. As always, voters will rank the candidates, and as in single transferable votes, if some candidate has a majority of the first place votes, then he or she is elected. But if no candidate has a majority, instead of dropping the candidate with the fewest first place votes, we'll drop the candidate with the lowest diversity score. Now, if there's a tie for lowest diversity score, then we'll look at the first place votes and we'll drop the candidate with the fewest first place votes. And then we continue until some candidate has a majority of first place vote. So it's very similar to single transferable voting, except that the rule for dropping a candidate is on the basis of diversity score rather than the number of first place votes. So what happens in our example? Well, no candidate has a majority of the first place votes, so we have to drop some candidates. We drop the candidate with the lowest diversity score. Sanders and Trump tie for the lowest diversity score. They each have a diversity score of 1. And so in this case, we drop Trump because Trump has fewer first place votes than Sanders. Trump has 29%, Sanders has 46%. So we drop Sanders. We drop Trump because Trump has fewer first place votes. But now the Bloomberg moves into first place for these voters. So now Bloomberg has a majority of the first place votes. So Bloomberg gets elected under this election scheme. Remember that Bloomberg is the Condorcet winner. So we're actually successfully electing the Condorcet winner by using this modified single transferable vote scheme. So that's good, but I want to go farther than that and show you that this voting scheme cannot be manipulated by strategic voting. And to do that, I'm making the following assumptions. I'm assuming, first of all, that the true preferences are single peaked. Of course, people are free to vote any way they want, but we'll assume that their true preferences are single peaked, and that each single peaked ranking is possible. And then finally, that when coalitions are voting strategically, they limit their rankings to one side of the Condorcet winner. I'll explain what I mean by that in a few minutes. So those are the assumptions, and under those assumptions, the conclusion is that no coalition of voters can gain by voting strategically. Let me show you why this is true. Let's look at our example here. So we saw that if voters vote truthfully, the rankings must look like this. So the Sanders supporters will rank Sanders above Bloomberg, above Trump. The Trump voters will rank Trump above Bloomberg, Sanders. The Bloomberg voters can vote, might have either this preference or this preference. Now, at the moment, we're not making any assumptions about what the preferences are, the percentages here. We're not making any assumptions about the percentages. Suppose that the percentages were such that Sanders is the Condorcet winner. And we have to show that that no one has the incentive to vote strategically if Sanders is the Condorcet winner. But if Sanders is the Condorcet winner, then then there actually must be a majority of voters with this ranking, because notice that these are the only voters who prefer Sanders to Bloomberg. These voters prefer Bloomberg to Sanders, so do these, so do these. So if Sanders is the Condorcet winner, more than 50% of voters must have this ranking. But if more than 50% of voters have this ranking, then clearly no one else can manipulate. They can't outvote a majority. So Sanders, in this simple case, manipulation is clearly never going to be worthwhile by any group. The Sanders voters aren't going to manipulate because they're getting their favorite candidate, and none of the others can change the outcome from being Sanders. So the more interesting case is, suppose that Bloomberg is the Condorcet winner when voters vote truthfully. Could the Sanders voters, for example, gain by manipulation? Well, the Sanders voters, remember, if the Sanders voters vote truthfully, they have a diversity score of 1. Suppose that some of the Sanders voters vote strategically, and they submit the ranking Sanders over Trump over Bloomberg. That will actually increase Sanders' diversity score from 1 to 2. And that means that Trump will be dropped because Trump is now the unique candidate with a diversity score of 1. Bloomberg has a diversity score of 1. Bloomberg has a diversity score of 2. Sanders has a diversity score of 2, thanks to this manipulation. Trump has a diversity score of just 1, so Trump gets dropped. But now Bloomberg takes over as the first place choice for these voters. Remember, we're using this modified single transferable vote. So Bloomberg will now have a majority of first place votes. So Bloomberg will still win even if the Sanders voters vote strategically. So the manipulation by the Sanders voters cannot pay off. And symmetrically, you might say, well, what if the Sanders voters pretended to have the ranking Trump, Sanders, Bloomberg? They could do that. That would increase Trump's diversity score, but now Sanders would get eliminated. So they certainly wouldn't want to do that. So the Sanders voters can't gain by manipulation, and the Trump voters can't gain by manipulation. The Trump voters can increase their diversity score if some of them submit the ranking Trump, Sanders, Bloomberg, so Trump's diversity score will go from 1 to 2. That will eliminate Sanders, but then Bloomberg moves into first place for these voters, and now Bloomberg beats Trump. Because remember, we're saying that Bloomberg is the Condorcet winner. So that means that all of these voters, a majority, prefer Bloomberg to Trump, and Bloomberg defeats Trump once Sanders is eliminated. So there are no manipulations that either the Sanders voters or the Trump voters can do to successfully stop Bloomberg from getting elected. Now there's one manipulation I haven't talked about, which which would be successful. So once again, these are the true preferences. Suppose that the Sanders voters, some of the Sanders voters manipulated by submitting the ranking Sanders, Trump, Bloomberg, and the other Sanders voters submit Trump, Sanders, Bloomberg. In other words, they would be increasing the diversity score of both Sanders and Trump. So now there's a three-way tie for diversity score. Sanders, Bloomberg, and Trump all have a diversity score of 2. Well, this is going to lead to the elimination of Bloomberg, because Bloomberg has the fewest first-place votes. And now it's a contest between Sanders and Trump, and Sanders wins because more people rank Sanders above Trump than Trump above Sanders. So this manipulation will pay off, but this is actually a very dangerous manipulation by the Sanders voters, because some of them are submitting Trump, Sanders, Bloomberg. If they submit too many of these, Trump will actually beat Sanders. So, which is terrible for the Sanders voters. They would rather have Bloomberg than Trump. So, yes, this is a possible manipulation, but in practice, it's a very complicated and very unlikely manipulation for Sanders voters to go through. So we're ruling that out by assumption, by saying that if you manipulate, you don't manipulate by submitting rankings to the left of the Condorcet winner and also to the right of the Condorcet winner. That's too complicated, and it's also too dangerous. Okay, so now I hope I've persuaded you that there actually is a voting system that will be resistant to manipulation, and it will elect the Condorcet winner. And furthermore, this voting system is unique in 3 senses. First of all, if we had some other voting system which elected a Condorcet winner, and this other system was also resistant to strategic voting, it would have to coincide with the voting system that we started with, in the sense that it would always elect the same winner regardless of manipulations. So in other words, what I showed you is the unique voting system that elects Condorcet winners and is resistant to strategic voting. But we can go farther than this. We might ask, well, suppose we wanted a system, suppose we know that preferences are single-peaked, could we devise some other voting system which is also strategy resistant when preferences are single-peaked? And the answer is, the answer is no. That is, if this other voting system did not elect a Condorcet winner, it could not be strategy resistant. So the only strategy resistant voting systems for single-peak preferences are ones that elect a Condorcet winner. We can't get strategy resistant for any other kind of election system. And finally, we might ask, well, if we expanded beyond single-peak preferences, could we get anything more? And the answer to that question is also no. There's no voting system on a superset of single-peak preferences which is resistant to strategic voting. I should have said that we're assuming that our voting systems are anonymous and neutral. They satisfy property A and N. Anonymous in the sense that all voters are treated symmetrically, and neutral in the sense that all candidates are treated symmetrically. Okay, I think rather than showing those results, I want to go to the empirical part of the paper. Most of the paper is theoretical, but as I said, we now have evidence based on American elections that voters' preferences really are single-peaked. Some years ago, the two American states, the states of Alaska and Maine, started using single transferable voting to elect their state officials, governor, state senator, state representative, and also for federal elections. So they're using single transferable vote for many elections. So we actually see, thanks to these elections, how voters are ranking the candidates. We know more than voters' favorite candidates. We know the whole ranking. And here is an example of an election that took place in Alaska 2 years ago. This was an election for the U.S. House of Representatives. Alaska is so small in population that it only has one representative. So this was the election for that one representative. There were 3 candidates. There was Sarah Palin, who was a far-right candidate, a Trump supporter. There was Nick Begich, who was a Republican, so conservative, but not very far to the right, so a moderate Republican. And there was a Democrat, a left-wing candidate, Mary Peltola. And here is the distribution of the ranking. So 18% of voters ranked Palin above Begich, and I'm leaving out the third candidate here because that can be inferred from the first two. So the third candidate here was Peltola. 14% ranked Begich above Palin. 8.5% ranked Begich above Peltola, and so on. Now, I claim that this distribution is actually very close to single peakness. There are 2 deviations. First of all, some voters only named their favorite candidate. They declined to rank the other 2. So see, look at these voters here. 11% of voters ranked Palin first, and they didn't rank Begich and Peltola. It's as though Begich and Peltola were tied for second place. Now, this is what we might call weakly single-peaked, where the truly single-peak preferences are these, where Palin is above Begich, because remember, Begich is closer to Palin in ideological space than Peltola is. Palin, Begich, Peltola is the strictly single-peaked ranking. This is weakly single-peaked, but if you go back to the argument that I made a few minutes ago, showing that with single-peak preferences, modified single transferable vote is resistant to strategic voting, that argument carries over to weakly single-peak preferences. These voters will not interfere with the argument I gave before, and these voters will not interfere with that, and these voters will not interfere with that. Now, there are some true violations of single peak preferences. Look at these voters here. These voters like the right-wing candidate best. They put the left-wing candidate second. So that's a violation of single peakness. Single peakness says that the moderate Republican should come second. And over here, these voters like the left-wing candidate, the Democrat, Peltola best, and they put the right-wing candidate, Palin, second. That's also a violation of single peakness. But notice that the fraction of voters who violate single peakness is tiny. 2% here, 2.5% here. And so if we change if we change the rules to say that in calculating diversity scores, a particular ranking has to get, say, 5% support in order to count toward a diversity score, this profile will work, because although this is a violation of single peakness, it won't count toward Peltola's diversity score. And although this is a violation of single peakness, it won't count toward Palin's diversity score.